One day in the not-so-distant future, you will walk outside, look up at the sky, and something will feel off. The stars will be familiar. The constellations you've known your whole life, Orion, Cassiopeia, Ursa Major, will still be there. But something will have changed. A new light will blaze in the heavens, outshining all others. Not a comet. Not a planet. A star that was once invisible to your eyes will suddenly be brighter than Venus, possibly even rivaling the glow of the moon. That day will mark one of the rarest, most astonishing cosmic events humanity has ever seen. This is not fiction. This is astronomy with a countdown. But before we continue, subscribe to the channel. Nestled deep within the faint constellation of Sagitta, or the Arrow, lies an unassuming patch of sky. If you were to gaze at it tonight with the naked eye, you'd see nothing unusual. Maybe you wouldn't see much at all. But hidden in that small sliver of the Milky Way is V Sagittae, a binary star system on the brink of destruction. Unlike the unpredictable flashes of supernovae or gamma-ray bursts that catch astronomers off guard, V Sagittae is unique. It has a deadline. And that deadline is around the year 2083. What makes this event so extraordinary isn't just that it will happen, it's that we know it will. Astronomers have studied this star for over a century, and what they've discovered is both terrifying and awe-inspiring. V Sagittae is headed for a catastrophic explosion, and that explosion will be visible from Earth with the naked eye. It won't just twinkle. It will blaze. For weeks, it may dominate the night sky like a celestial beacon, a cosmic firework we can all watch unfold in real time. For centuries, stargazing has been about looking back in time. The light from distant galaxies takes millions, sometimes billions of years to reach us. Every time we peer into space, we're seeing echoes of the past. But with V Sagittae, something different is happening. We are not just observing history, we are predicting the future. We are standing on the edge of a celestial countdown clock, ticking louder with each passing year. The uniqueness of V Sagittae lies in its inevitability. It's not a question of if it will go nova. It's a question of when. This is not just an astronomical footnote, it's a story of anticipation. Of watching a ticking time bomb float silently in the sky, knowing that it will one day erupt in a spectacle unmatched by anything else in the night. It challenges our perception of time. Most cosmic phenomena operate on scales that far exceed human lifetimes. Stars are born, live, and die over millions or billions of years. But V Sagittae? Its climax is scheduled within the next few decades. The children born today may be adults when it explodes. Some of us may live to see it. That proximity in time gives it an almost mythic resonance. It's like standing before a volcano that hasn't erupted in millennia, knowing the magma is beginning to churn beneath. And this ticking clock is no metaphor. It's measurable. Astronomers have tracked its increasing brightness over decades and mapped its acceleration. They've witnessed its orbital dynamics speeding up, its mass transfer rate increasing, and its instability mounting. Every bit of data confirms the same chilling conclusion: we are approaching the end. There is something inherently poetic about this event. A star system, too faint for most of us to notice, is preparing its final act, and it's an act so loud, so bright, that it will command the attention of the entire world. This is not some distant galaxy, hundreds of millions of light-years away. This is within our Milky Way. Roughly 7,800 light-years from Earth, V Sagittae resides in our cosmic neighborhood. And when it goes off, no telescope will be needed. You'll simply have to look up. But before we get to the firestorm, we must understand what makes this star system so remarkable. What is V Sagittae? Why is it so unstable? Why now? What does it mean to go nova? And how can we possibly predict an explosion with such precision? These questions pull us into one of the most fascinating stories the cosmos has to offer. From stellar cannibalism to orbital death spirals, from thermonuclear ignition to front-row cosmic fireworks, the journey of V Sagittae is a lesson in astrophysics, fate, and beauty. So let us begin by exploring what it means to live under a sky that we know will change. The night sky has always been a canvas of quiet brilliance, pinpricks of light suspended in an ocean of darkness. We measure its beauty and subtlety, the cool gleam of Sirius, the steady shine of Jupiter, the faint shimmer of distant galaxies for those with telescopes and patience. But when V Sagittae erupts, the night will forget its subtleties. For the first time in living memory, the sky will be dominated by a new, blazing point of light, so bright, so sudden that millions will look up and wonder if it's a new planet, a satellite gone rogue, or something far stranger. This won't be a distant supernova seen only with long exposures and sophisticated instruments. It will be a naked-eye event, visible to all, from every corner of the planet. On that day, the brightest star we currently know, Sirius, will be outshone. V Sagittae could reach magnitude -2 or even brighter, depending on how the explosion unfolds. For comparison, Sirius shines at around magnitude -1.5 on average, and Venus, our brightest planet, can peak around -4.7. The Moon, of course, sits far brighter, but if conditions align just right, V Sagittae's nova could rival even that for a brief, breathtaking moment. Imagine stepping outside and seeing a second star, near the Moon, piercing and brilliant. It will not twinkle like the others. It will command attention. News broadcasts will erupt with explanations. Social media will overflow with photos and conspiracies. People will remember where they were when it appeared. It will feel otherworldly, because in a sense it is. The brightness of V Sagittae's eruption will come not from size, but from the sheer energy of thermonuclear ignition. When the white dwarf collects enough material from its companion star, the pressure and temperature on its surface will reach the point of runaway fusion. It's not a slow burn, it's a sudden, violent flash, like lighting a match on a powder keg. That release of energy will hurl material into space and unleash an extraordinary burst of light. The light will travel 7,800 light-years to reach us, but when it does, it won't be a whisper. It will be a roar. For many who have never seen a shooting star, let alone a nova, this will be their first introduction to the dynamic violence of the cosmos. It will break through the haze of city lights. It will be seen in places where stars have been all but drowned out. It will make astronomers and poets alike stop and wonder. And it will not be fleeting. Unlike meteors, which burn out in seconds, or comets, which drift slowly across the sky, V Sagittae's nova will persist. For days and nights, and possibly even weeks, this new light will remain, slowly fading, but never suddenly gone. Children will make wishes on it. People will give it names. Some might believe it to be an omen, as humans once did with every rare light in the sky. But what it truly represents is a moment when the heavens remind us how alive they really are. In ancient times, such an event would have been considered supernatural. Civilizations would have recorded it on clay tablets or carved it into stone. In the 11th century, the appearance of the Crab Nebula's progenitor supernova was recorded by Chinese astronomers, seen even during the day for nearly a month. V Sagittae may well echo that moment, a modern cosmic phenomenon with a historical footprint. The difference now is that we are prepared. We know it's coming. And with that knowledge comes a rare emotional anticipation. We aren't just witnesses, we are expectant. Waiting. Watching. We've circled the date in the cosmic calendar and are holding our breath. And when the night finally brightens with a light not seen before, it won't be just an astronomical event, it will be a global one. A reminder of our shared sky. A beacon that transcends. A luminous exhale from the universe, echoing across millennia. That night, the brightest night in living memory, will mark one of the rare times when the universe writes a story not in textbooks, but in the sky itself. To understand the significance of V Sagittae's impending outburst, we must look beyond the light it will eventually emit. We must peer into its heart, into the system itself. Because V Sagittae is not a solitary star waiting to die. It is a binary system, two stars, gravitationally locked, orbiting each other in a relationship that is as deadly as it is fascinating. It is this relationship that defines everything that follows. When people hear, "A star will explode," they often imagine a single, dying giant collapsing under its own weight. But V Sagittae's story is more complex, and far more dramatic. It's not about a lone star reaching the end of its life, but about an interaction between two very different stellar bodies, a white dwarf and a main sequence star, spiraling around each other in a dance that grows tighter with every passing moment. The white dwarf is the remnant of a star that was once much like our Sun. After exhausting its nuclear fuel, it shed its outer layers and left behind a dense, hot core. A white dwarf is extraordinarily compact. Imagine the mass of the Sun squeezed into a volume roughly the size of Earth. Incredibly dense. Incredibly hot. But no longer undergoing fusion. It is, in essence, a stellar corpse. However, under the right circumstances, even a dead star can reignite. The main sequence star, its companion, is still in the prime of its life. It fuses hydrogen into helium in its core, just as our Sun does. But compared to the white dwarf, it is bloated and relatively diffuse. It is larger in size, but less massive. This imbalance sets the stage for everything that follows. Over time, as the two stars orbit each other, the white dwarf's immense gravitational pull begins to siphon material from its companion. Like a vampire drawing life from its victim, it steals hydrogen-rich gas, pulling it onto itself via an accretion disk, a swirling spiral of gas that falls inward with increasing speed and heat. This process is not gentle. It is violent. The material slams into the white dwarf's surface at tremendous velocities, heating the star and compressing the gas layer by layer. Over time, this accumulation builds up pressure, setting the stage for the nova to come. But this is not a stable relationship. This is not the peaceful give-and-take seen in some binary systems. This is a death spiral. What makes V Sagittae even more extraordinary is the sheer imbalance in its mass exchange. Most binary systems that exchange material reach a kind of equilibrium. The more massive star donates mass to the smaller one until the mass ratio stabilizes. But V Sagittae doesn't follow this rule. The rate at which material is being transferred is not decreasing, it's accelerating. The main sequence star is giving more and more of itself to the white dwarf, and the gravitational pull between them is causing their orbit to decay. They complete a full orbit in just 12.3 hours, an incredibly tight and fast interaction. That rapid period tells astronomers something vital. The system is losing angular momentum. In simple terms, the two stars are spiraling inward. Closer and closer. Faster and faster. Until eventually, the mass transfer reaches a critical point and the entire system becomes unstable. In the case of V Sagittae, the white dwarf is not just collecting gas, it's preparing for ignition. At some point in the near future, the amount of stolen hydrogen will reach a threshold. When it does, the temperature and pressure will become so extreme that nuclear fusion reignites, not in a stable, star-like way, but in a runaway reaction. A thermonuclear flash will erupt across the white dwarf's surface, unleashing a tidal wave of light and energy. That is the nova. That is the moment everything changes. This system is a kind of natural laboratory. A place where we can study the physics of extreme mass transfer, gravitational dynamics, orbital decay, and thermonuclear instability. And the fact that this is all happening in a system we've known about for more than a century, that we can predict its outcome, is something truly rare in astrophysics. V Sagittae's binary nature is the key to its fate. Without the interplay of these two very different stars, this event would never happen. The white dwarf alone would simply cool into darkness. The main sequence star alone would continue its long, steady burn. But together, they form a catastrophic duet, a gravitationally bound system marching toward detonation. And perhaps most remarkably, it's not just the physics that's compelling, it's the emotional weight of it. The idea that this star we will one day see erupt in our sky is the product of a long, slow cosmic tragedy. A quiet, deadly romance between two stars that ends in fire. The true violence of V Sagittae lies not in the moment of its explosion, but in the slow, methodical process leading up to it, a process happening right now, silently, invisibly, far above our heads. This is a story of celestial cannibalism, of one star consuming the flesh of another, piece by piece, gas by gas, until it reaches a threshold from which there is no return. It is this process that earns V Sagittae one of its most chilling titles, the cosmic cannibal. In a typical binary star system, gravitational balance and orbital dynamics create an equilibrium where both stars can exist and evolve without interfering much in each other's life cycles. But V Sagittae doesn't operate by those rules. It is fundamentally unstable. The white dwarf, though smaller in size, is vastly denser and far more gravitationally powerful than its companion. It exerts such an immense pull that it literally rips hydrogen from the outer layers of the main sequence star, forming a swirling accretion disk that funnels gas down onto its own surface. This is not a voluntary transfer of material. This is theft at a cosmic scale. From a distance, the system might look like two glowing dots orbiting each other in perfect synchronization. But zoom in closer, and the true horror begins to emerge. The companion star is being deformed, its surface stretched into a teardrop shape by the gravitational grip of the white dwarf. A stream of gas flows from the point of greatest distortion, called the Lagrangian point, spilling into the void, arcing across space, and wrapping itself around the white dwarf in a spiraling torrent of stolen matter. And what happens to that matter is even more dramatic. As gas accumulates on the white dwarf's surface, it doesn't simply rest there. It is compressed under immense gravity, layer after layer piling up. The outer layers of this growing envelope heat rapidly, reaching temperatures of hundreds of thousands to millions of degrees. This isn't a gentle warming. It is pressure cooker physics, the kind of environment where atoms are smashed together with such force that new elements begin to form. Yet even with all this tension building, the white dwarf doesn't react, at least, not yet. It continues to feed, silently and without release, biding its time as it approaches the Chandrasekhar limit, the critical mass threshold beyond which a white dwarf cannot remain stable. That limit, approximately 1.4 times the mass of our Sun, represents a boundary between continuation and destruction. While V Sagittae's white dwarf may not cross this limit in its upcoming event, it's not yet fated for supernova. Its growing mass is pushing it toward thermonuclear instability. This process, known as runaway hydrogen fusion, is the true time bomb within V Sagittae. When the pressure and temperature on the white dwarf's surface reach the ignition point, the hydrogen doesn't fuse slowly and steadily as it does in a normal star. Instead, it ignites all at once, in a thin, explosive shell surrounding the white dwarf. The result is a nova, a massive detonation that ejects the accumulated material outward at high velocity, creating a flash of light so intense it can be seen from across the galaxy. But this is not a one-time meal. The white dwarf's cannibalism is ongoing. It consumes, explodes, and then returns to its hunger. In many nova systems, this cycle can repeat, depending on how much mass is available. But what makes V Sagittae especially fascinating is the increasing pace at which this is all happening. Observations over the last few decades have shown that the rate of mass transfer is not just steady, it is accelerating. This acceleration isn't random. It's a symptom of deepening instability. As the white dwarf grows more massive, its gravitational pull strengthens, dragging more and more gas from its companion. That companion, meanwhile, is growing smaller and more distorted, unable to resist the siphoning. Their orbit, once stable, is now collapsing. The period of rotation between them is shrinking, a cosmic clock winding itself faster and faster. In the past century, astronomers have watched as the brightness of V Sagittae gradually increased. That increase is a byproduct of this mass transfer process. More matter means more heat, more radiation, and more turbulence within the accretion disk. It's not just the white dwarf glowing, it's the entire system flaring with energy as the gas spirals in at ever-increasing rates. From Earth, this is the glow of doom. An early warning. We're watching a predator fatten itself before the kill. And while the white dwarf's feast may seem slow on human timescales, in cosmic terms it is astonishingly rapid. Systems like this usually evolve over millions of years. V Sagittae is changing over mere decades. The term, cosmic cannibalism, is no exaggeration. It's a fitting metaphor for a process that is at once beautiful and brutal. There is something undeniably dramatic about a star that devours another, not with claws or teeth, but with gravity, a slow-motion consumption powered by fundamental forces of the universe. The fate of the companion star is sealed. As it loses mass, it becomes even more unstable. Eventually, it will give up so much of itself that the remaining core may collapse, or the two stars may merge entirely, triggering a cataclysmic reaction far more powerful than anything we've yet seen. If the white dwarf ever does exceed the Chandrasekhar limit, that would trigger a Type I supernova, an even more violent death that obliterates the white dwarf completely. But in the case of V Sagittae, that may be farther down the timeline. For now, the imminent explosion is classified as a nova, and the system is approaching that stage with increasing speed. This cannibalistic phase is its final act before ignition. The last stage in a cosmic process that began when two stars found themselves in a gravitational bond that would doom them both. It's strange to think that something so catastrophic is happening right now, quietly above our heads. That somewhere in the constellation of Sagitta, one star is swallowing another, preparing to light up the night sky with its final breath. No human action can influence it. No intervention can stop it. It will happen, exactly as the laws of physics dictate. But the knowledge of this inevitability grants us something rare, a front-row seat to the drama of the universe, written in forces we can understand, playing out across a canvas of darkness and stars. V Sagittae is not just a star system. It is a story, and like all great stories, it builds toward a climax. That climax will come in the form of a fireball brighter than anything we've seen in our skies for generations. And behind that brightness lies this quiet, relentless process of consumption, a cosmic predator feeding on the light of another. In most binary star systems, there's a balance, an intricate gravitational dance where two stars orbit a shared center of mass, tugging at each other but ultimately maintaining a kind of cosmic equilibrium. Some binaries exist peacefully for billions of years, exchanging energy and matter at manageable levels or not interacting at all. But V Sagittae doesn't fit that mold. Its story is not one of balance, but of decline. Its partnership isn't graceful, it's decaying. What began as a gravitational duet is rapidly becoming a death spiral. The stars are drawing closer and closer, locked in an unstable relationship that can only end in catastrophic release. V Sagittae's instability lies in the very core of its mechanics. Binary systems typically evolve in one of three ways. They either remain detached, with no mass transfer. They engage in stable mass transfer where one star donates gas to the other at a sustainable rate. Or, as in the case of V Sagittae, they become contact binaries, systems where the two stars spiral so close together that their gravitational fields overlap and the mass transfer becomes uncontrollably rapid. This is where the chaos begins. In V Sagittae's case, the white dwarf and its companion are orbiting each other roughly every 12.3 hours. That means that every half-day on Earth, these two stars complete an entire revolution around one another. That kind of orbital period implies incredible proximity, closer than Mercury is to the Sun, closer than many stars and binary pairs are allowed to be without beginning to merge. And as this orbit shrinks, the transfer of material speeds up. The more matter the white dwarf pulls in, the more massive and gravitationally dominant it becomes, and the faster the two stars revolve around each other. This leads to a feedback loop, an inherently unstable one. As the white dwarf accretes more matter, it gains mass and tightens the orbit further. A tighter orbit leads to more intense gravitational interaction, which in turn leads to an even faster rate of mass transfer. This spiraling feedback loop doesn't level off. It accelerates. Over the last several decades, astronomers have recorded a dramatic exponential increase in the system's overall brightness. This isn't just a slow rise, it's a curve that steepens with each passing year, matching the physics of an inward spiraling binary system preparing for explosive collapse. Unlike more balanced binaries, where mass transfer stabilizes due to regulatory forces such as angular momentum loss or magnetic braking, V Sagittae appears to be in what's called a dynamically unstable mass transfer phase. In this phase, the mass donor, the main sequence star, is so affected by the loss of its own material that it starts to expand and lose matter even faster, creating a runaway effect. It's not just being pulled, it's being torn apart by its own imbalance, unable to stop itself from contributing to the cataclysm that's coming. One of the strangest ironies of V Sagittae's system is that the larger, seemingly dominant star, the main sequence companion, is the one being consumed, while the much smaller, seemingly weaker star, the white dwarf, is the predator. This inversion of expected roles is a direct result of the extremes of density and gravity. The white dwarf may be compact, but it's a powerhouse of gravitational force. That compactness gives it leverage. And with that leverage, it can strip away layers of its companion's outer envelope, turning the relationship from mutual orbit into parasitic dependency. The instability also affects the orbital energy of the system. As gas is transferred from the companion to the white dwarf, the loss of angular momentum causes the two stars to fall inward. It's not simply a case of spinning faster, it's a literal reduction in the distance between the two stars. Picture two figure skaters spinning while holding hands. As they pull each other in, their rotation speeds up. In V Sagittae's case, this acceleration is not optional. It's a natural consequence of physics, and one that leads inexorably to a final collision or detonation. Moreover, the presence of an accretion disk around the white dwarf, a swirling halo of superheated gas funneled from the main sequence star, further destabilizes the system. This disk is not just a passive reservoir of matter. It's an energetic, chaotic structure, prone to instabilities of its own. Shocks, turbulence, and friction within the disk can lead to sudden bursts of light or increases in X-ray and UV radiation. These flare-ups are more than just observational oddities. They are real-time indicators that the system is becoming more and more volatile. Some astronomers suspect that V Sagittae may not just go nova once. If enough mass is retained by the white dwarf after the initial eruption, future nova events could occur. Alternatively, if the mass transfer continues long enough to push the white dwarf's mass past the Chandrasekhar limit, it could result in a Type I supernova, a far more powerful and destructive event that would obliterate the white dwarf entirely. In either scenario, what's certain is that stability is no longer part of the equation. The system has crossed into a terminal phase. This kind of instability is rare. Most nova events we observe in the galaxy are not predicted. They're discovered only after the explosion has already begun. But V Sagittae gives us a rare glimpse into what happens just before a nova, and it allows scientists to watch, in real time, the unraveling of a stellar system that is doomed. It's like observing the slow cracking of ice over a deep lake. You don't know the exact moment it will shatter, but you know that it will. We often think of stars as stable, fixed points of light, unchanging across the centuries. But V Sagittae reminds us that stars are dynamic. They evolve. They interact. And in some cases, they destroy each other. The unstable relationship between the two components of V Sagittae is like a fuse, one that has been lit and is now burning rapidly toward detonation. The incredible thing is, we can see it burning. We can chart its progress. And we know where it leads. There is something deeply unsettling and yet profoundly fascinating about this. To witness a star system not just exist, but die in real time, on a human timescale, is almost unheard of in astronomy. V Sagittae is an anomaly in that sense. A cosmic time bomb with a countdown measured not in millions of years, but in mere decades. That gives it a special place in the sky, and in our story as observers of the universe. It is not just a scientific curiosity. It is a celestial drama we are all privileged to witness unfold. There are few things in the cosmos that move fast enough to challenge our perception of celestial time. The universe typically operates on scales of millions or billions of years, where stars live and die across epochs that dwarf human history. But every so often, something bucks the trend, something accelerates, changes, and evolves right before our eyes. V Sagittae is one of those rare anomalies. And in recent decades, it has begun racing toward its fate, faster and faster, like a train picking up speed down a track with no brakes. This race is measurable, observable, and unmistakable. The clearest indicator? Its exponential increase in brightness. Historically, V Sagittae was catalogued as just another variable star, one of the countless flickering points in the sky whose brightness fluctuates due to internal or external mechanisms. It was first discovered in 1902, noted as a faint and unimposing object in the tiny constellation of Sagitta. But by the latter half of the 20th century, astronomers began noticing something strange. The changes in brightness were not random. They were increasing. At first, the growth was slow and subtle, well within the bounds of ordinary stellar behavior. But over the years, it became unmistakable. The system was brightening at an accelerating rate. Now, brightness alone doesn't necessarily mean catastrophe. Many variable stars brighten and dim due to pulsations, star spots, or eclipsing companions. But V Sagittae's behavior didn't fit any known pattern. The light curve, the graph that charts its changing brightness, didn't follow a sine wave or a periodic fluctuation. It followed an exponential curve. That kind of mathematical progression is incredibly significant. It means that each year, the rate of change is faster than the year before. It's not a steady climb, it's a steepening slope. And in astrophysical terms, that's a red flag. Brightness in a star system like this is directly tied to energy output, and energy output is in turn tied to processes like mass transfer, accretion, and disk activity. The brighter V Sagittae gets, the more active its mass transfer has become. The more active the mass transfer, the closer the system moves toward thermonuclear instability. In other words, the increasing light is a visible sign of doom, a beacon announcing that the system is spiraling toward detonation. By the 1990s, the brightness of V Sagittae had already doubled from earlier observations. But that was just the beginning. In the 2000s, it increased even more. And now, in the 2020s, it continues to climb at a rate that defies long-term stability. Astronomers have used decades of photometric data, from both professional observatories and dedicated amateur astronomers, to model this trend. And the conclusion is both chilling and awe-inspiring. The system is approaching an exponential tipping point, one that predicts a major nova event around the year 2083, give or take a few years. This estimate is not pulled from thin air. It's based on carefully calibrated light curves, historical data, accretion models, and simulations of binary star evolution. And while nature can be unpredictable, the math is compelling. If current trends continue, the system will reach a state where the amount of gas piled onto the white dwarf's surface crosses a thermonuclear threshold. That threshold, while varying slightly depending on composition, is remarkably consistent across systems. Once reached, the white dwarf will erupt, ejecting much of its stolen material in a brilliant outburst of light and energy. The build-up toward this point is what makes V Sagittae's case so extraordinary. In most nova systems, we only catch them after they go off, when the light suddenly flares and alerts observers to the event. We rarely get to watch the slow approach. But V Sagittae is different. We're seeing it warm up before the explosion, like a star breathing faster and faster before a final scream. And there are other symptoms besides brightness. The orbital period is decreasing, meaning the stars are spiraling inward. Their distance is shrinking. Their gravitational interaction is intensifying. All of this contributes to further destabilization. The accretion disk glows brighter with each added layer of gas. And with more mass being dumped onto the white dwarf's surface every day, the countdown clock ticks a little louder. Some models suggest that the system may begin to emit high-energy radiation, X-rays, UV light, and even gamma rays, in the years just before the nova. This pre-eruption activity will provide additional clues, allowing astronomers to fine-tune their estimate and possibly even predict the explosion within a narrow window of months or weeks. If that prediction holds, we could one day issue an alert to the world: look up tonight. The sky is about to change. That level of predictive power is unprecedented in the study of nova events. It's a bit like forecasting a volcanic eruption with pinpoint accuracy, a feat rarely achieved, yet invaluable when successful. V Sagittae gives astronomers the chance to do just that. And because we've been watching its brightness rise for decades, we have a rich archive of data that can inform everything from nova physics to gravitational dynamics to stellar evolution modeling. But it's not just a scientific curiosity. For the public, the growing brightness will eventually become visible even without instruments. Right now, V Sagittae is still too faint for most observers to see unaided. But by the time of the eruption, it will be a naked-eye object. Possibly even visible during the day if the nova reaches peak brightness. And unlike fast-moving meteors or short-lived eclipses, this event will linger. The bright phase may last for weeks, giving people around the world the chance to see it with their own eyes. No telescope, no app, no filter. Just the raw spectacle of a dying star screaming its final breath across the sky. This idea, that we are watching a celestial object race toward its death in real time, adds an emotional weight to the story. For once, we're not just analyzing the past. We're anticipating the future. V Sagittae is not ancient light from a star that exploded eons ago. It's a live feed of a catastrophe slowly unfolding before our very eyes. It's a rare feeling in astronomy, this sense of urgency. Most celestial events have already happened, and the light takes so long to reach us that by the time we see them, the moment is long gone. But not here. With V Sagittae, we are watching the fuse burn down, not in imagination, but in reality. Every increase in brightness is a tick of the clock. Every year that passes brings us closer to detonation. And when the moment comes, when the brightness spikes and the light explodes outward into the void, we will know that we saw it coming. That we stood beneath the stars, looking up, and bore witness to the end of a system that had warned us all along. One of the most astonishing aspects of the V Sagittae story is not just that it will erupt, but that we can predict it. In a universe governed by chaos, governed by incalculable scales and incomprehensible timelines, the idea that we can mark our calendars for the eruption of a star is almost unthinkable. And yet, here we are, peering at a system thousands of light years away, watching its light climb faster and faster, and realizing that we are just decades away from a cosmic event unlike anything seen in centuries. Predicting a nova is no easy feat. Most novae are discovered by accident. An unexpected brightening in a patch of sky, noticed by an astronomer or even an amateur observer, then later identified as a white dwarf erupting after a critical accumulation of hydrogen. These events are sudden, brief, and typically occur in systems too distant or too faint to monitor regularly. But V Sagittae is the exception. We are not stumbling upon it after the fact. We are watching it wind up. The prediction that V Sagittae will go nova around the year 2083, give or take a few years, is the result of decades of observations and sophisticated modeling. Astronomers have tracked the system's increasing brightness with great precision. Photometric records from as far back as the early 20th century show a slow but undeniable trend, a dim variable star growing steadily more luminous over time. But it's the recent data from the last few decades that really changes everything. Using modern ground-based observatories and data from sky surveys, researchers began charting the exact rate of brightness increase. They discovered something remarkable. The light curve of V Sagittae follows an exponential trajectory. This is more than just a rising slope, it's a curve that accelerates, steepens, and indicates a self-reinforcing system growing more and more unstable with each passing year. Once plotted, this curve doesn't just suggest a future eruption, it demands it. Astronomers at Louisiana State University, who led much of the modern predictive analysis, concluded that if the brightness continues on its current trajectory, the system will reach nova conditions in the mid-2080s. Their models point specifically to around the year 2083 as the most likely window, although they acknowledge the nature of such predictions includes uncertainty, give or take a few years, depending on factors such as the exact rate of mass transfer, the composition of the accreted material, and the temperature gradient on the white dwarf's surface. This kind of forecasting relies heavily on our understanding of the nova mechanism itself. In a system like V Sagittae, the white dwarf pulls hydrogen-rich gas from its companion until enough material builds up on its surface. When that hydrogen reaches a certain pressure and temperature threshold, it ignites in a thermonuclear runaway. This ignition doesn't destroy the white dwarf. Instead, it blasts away the accumulated shell of gas in a massive eruption of light and matter. The white dwarf survives, and the cycle can potentially repeat over thousands of years. But V Sagittae is not your average nova. Its current rate of mass transfer is increasing, not stable. It is possible that the 2083 event may not be a simple nova but the beginning of something even more extreme, perhaps a merger, or a prelude to a more powerful detonation down the line. This is what makes the prediction so significant. We're not just estimating the timing of a flash in the sky, we're potentially forecasting the beginning of a complete transformation of the system. One might wonder how accurate such predictions can really be. After all, stars are not clocks. They don't tick in mechanical precision. They are governed by physics, yes, but physics can be complex, chaotic, and sensitive to initial conditions. That's why astronomers are constantly refining their models, incorporating new observations, measuring the orbital decay rate, checking for fluctuations in the light curve, and looking for telltale signs like changes in spectral lines that indicate shifts in temperature, velocity, and gas composition. Interestingly, V Sagittae is not the only system whose eruption has been predicted, but it is one of the few we've caught early enough to observe in such detail before the event. In this way, it serves not just as an impending spectacle, but as a proving ground for our theoretical models. If our predictions about V Sagittae are accurate, it validates a whole class of simulations related to binary evolution, accretion physics, and the timing of explosive events. That means the implications of this prediction stretch far beyond a single star system. They extend to our broader understanding of how stars live, die, and interact with one another. This predictive capability also gives humanity something rare, a cosmic appointment. We are used to looking backward in time when we observe the sky. The light from distant stars is ancient. When we gaze at the Orion Nebula or the Andromeda Galaxy, we are seeing light that began its journey long before human civilization even existed. But V Sagittae flips that paradigm. Instead of looking back, we are looking forward. We know it will explode. We know it will brighten the sky. And we know that it will happen soon, within the lifetime of many people alive today. It creates a strange sense of anticipation. For the first time in modern astronomy, we're not just reacting to a cosmic event, we're planning for it. Schools will prepare lessons. Telescopes will be pointed. Cameras will be ready. Skywatchers across the globe will have a rare chance to witness a nova with their own eyes, without the need for specialized equipment or dark skies. And that kind of shared experience is incredibly rare in the realm of deep space. There's also the profound psychological impact to consider. In a world where so many celestial events feel remote or intangible, the idea that we can set a date, roughly, for a star's eruption gives us a tangible connection to the cosmos. It's something to look forward to, not with fear, but with awe. A reminder that we are not just passive inhabitants of a quiet world, but participants in an evolving, energetic universe. And perhaps, when the moment finally arrives, when V Sagittae erupts and its light floods the night sky, it will serve as a unifying moment, a flash of brilliance that transcends. But until that day comes, we will watch. We will measure. We will refine our predictions. And we will wait, knowing that for once, we are not just spectators of a cosmic past, but witnesses of a cosmic future already unfolding. To fully understand what's about to happen to V Sagittae, we must first understand the phenomenon that will transform it from an ordinary point of light into a blazing object brighter than any other star in the night sky, a nova. Despite how it sounds, a nova is not a new star. It is not the birth of something, but a violent rebirth, a fiery resurgence from the core of a dead star that temporarily reignites in a thermonuclear blaze. And while it may not rival the sheer destructiveness of a supernova, its spectacle and power are no less dramatic. At the heart of a nova is a white dwarf, the remnant core of a star that once burned like our sun. After exhausting its nuclear fuel, a medium-sized star sheds its outer layers and contracts under its own gravity into a tiny, dense object. A white dwarf is incredibly compact, typically only the size of Earth, yet containing a mass up to 1.4 times that of the Sun. That density creates a gravitational field strong enough to bend light and steal gas from any nearby companion star. And this is exactly what's happening in the V Sagittae system. Over time, as the white dwarf pulls in hydrogen-rich gas from its companion through a process known as accretion, the stolen material begins to accumulate on its surface. But the white dwarf is no longer undergoing core nuclear fusion. It cannot simply burn this new hydrogen layer in a controlled fashion. Instead, the gas continues to pile up, compressing under the immense weight of the dwarf's gravity. The pressure rises. The temperature climbs. And then, when the right critical point is reached, everything ignites. The result is a runaway thermonuclear reaction, triggered not in the core, but on the surface of the white dwarf. Hydrogen fuses explosively into helium in a thin shell, releasing an enormous amount of energy in a very short time. The energy of this detonation blows away the outer layer of gas that had built up, ejecting it into space at thousands of kilometers per second. That sudden release of matter and energy is what we see from Earth as a nova, an apparent, new star, that wasn't visible before or was much dimmer, now flaring to brightness that can rival the most luminous objects in the sky. The term, nova, comes from the Latin word novus, meaning new, because early skywatchers interpreted these sudden appearances as the birth of a new celestial body. But in reality, a nova is the echo of an old star, violently reminding the universe it's not done yet. It is a resurgence, not a genesis. A typical nova can increase the brightness of a star by 10,000 to 100,000 times its original magnitude. That's a massive jump, especially when you're dealing with a star that was once invisible to the naked eye. In V Sagittae's case, astronomers believe the explosion will cause it to briefly outshine Sirius, Venus, and perhaps even rival the brilliance of the full moon. It may become visible in the daytime sky, a rare feat for anything beyond our solar system. Importantly, a nova is not the same as a supernova. The latter is a total destruction event, where a star dies in a final, cataclysmic collapse that leaves behind a neutron star or black hole, or in some cases obliterates itself entirely. A nova, by contrast, is survivable. The white dwarf remains intact, often ready to repeat the process. In fact, some systems, called recurrent novae, experience multiple outbursts over time as the cycle of accretion and ignition repeats. But V Sagittae may not be a typical recurrent nova. Because of its extraordinarily high rate of mass transfer and increasing instability, this may not be just another explosion in an ongoing sequence. It may be the defining moment for the system, a transition phase, or even the last nova before a merger or a supernova occurs in the distant future. It's a threshold event, and one that's being driven entirely by the physics of nova formation. The energy released in a nova is immense, though not enough to disrupt the white dwarf itself. The expelled gas forms a shell that moves outward into space, creating beautiful, glowing clouds of ionized hydrogen, often visible in telescopic images as intricate, ring-shaped remnants. These nova remnants can persist for centuries, gradually fading as the material disperses into the interstellar medium, enriching it with elements that may one day form new stars, planets, and even life. From a scientific perspective, novae are invaluable laboratories. They provide insight into the physics of thermonuclear ignition, accretion disk behavior, and binary evolution. They also help us refine our understanding of stellar life cycles, particularly for systems on the edge of instability like V Sagittae. And because novae are relatively common in our galaxy, dozens are discovered each year, they serve as test cases for validating astrophysical models. But what makes V Sagittae special is that we aren't watching a nova after it happens. We're watching it before. This gives astronomers an unprecedented opportunity to study the prenova state of a system in exquisite detail. We can measure the increase in brightness, track changes in the orbital period, monitor the mass accretion rate, and even detect spectral signatures that hint at the composition of the incoming gas. This is real-time astronomy at its finest, predictive, precise, and profoundly thrilling. When V Sagittae goes nova, it will carry that same symbolism, but amplified. Because this time, we're not merely reacting to the event. We are expecting it. We understand what it is, what causes it, and why it matters. That knowledge transforms the nova from a mystery into a moment of shared cosmic understanding. So what is a nova? It is the echo of a dead star's hunger. It is the fire that comes not from youth, but from decay. It is the dramatic consequence of stellar theft, a brief, brilliant cry from a system on the edge of destruction. It is a cosmic alarm clock that doesn't tick, but explodes. And for V Sagittae, that explosion is no longer a question of if. It is only a matter of when. While V Sagittae's eventual explosion will not rise to the level of a supernova, a titanic event that can outshine entire galaxies, it will still be a phenomenal, sky-shaking detonation by every earthly standard. It will be one of the most powerful and luminous stellar eruptions visible in our lifetime, rivaling some of the most brilliant natural spectacles humanity has ever witnessed. And despite not destroying the white dwarf at its heart, the energy unleashed will be immense, painting the night with fire and turning a forgotten star into a household name. To put things into context, a supernova is the full-scale obliteration of a star. It occurs when a massive star collapses in on itself or when a white dwarf exceeds the Chandrasekhar limit, roughly 1.4 times the mass of the Sun, and can no longer support its own mass. That collapse releases an unfathomable amount of energy, so much, in fact, that it can release as much light in a few weeks as our Sun will emit in its entire lifetime. The result can be neutron stars, black holes, and supernova remnants that stretch for light years. A nova, on the other hand, does not involve this kind of total destruction. In a nova event, as with V Sagittae, the explosion is confined to the outer layer of material that has been accumulating on the surface of a white dwarf. When this gas ignites in a runaway thermonuclear reaction, it blasts away into space, shedding mass and energy in a flash that can temporarily increase the system's brightness by thousands or tens of thousands of times. But the white dwarf itself remains intact, though scarred, and ready to start the process all over again. Yet this distinction between nova and supernova shouldn't fool anyone into thinking that a nova is tame. On a cosmic scale, it is still a detonation. The explosion will eject an enormous amount of gas at high velocities, often in the range of 1,000 to 4,000 kilometers per second. That's fast enough to cross the entire diameter of the Earth in under 10 seconds. The amount of energy released in a classical nova event is on the order of 10 to the power of 44 ergs, roughly 1 million times the total energy output of an average hydrogen bomb. For V Sagittae, the power will be even greater. Its accretion rate is among the highest of any known nova progenitor. The companion star is dumping an extraordinary volume of hydrogen onto the white dwarf. The system is spiraling inward, increasing pressure, accelerating mass flow, and tightening its orbit to extremes. This means that when the detonation finally occurs, it will not be a typical nova, it will be an exceptionally luminous one. Astronomers anticipate that V Sagittae could reach an apparent magnitude of -2 or brighter during the peak of its explosion. This would make it more luminous in the sky than Sirius, the current brightest star at magnitude -1.46, and possibly even brighter than Venus, which typically hovers around -4. In the most optimistic scenarios, the nova could briefly rival the full moon in brightness, especially under dark, clear skies. That kind of magnitude would make V Sagittae a dominating presence, visible not just to seasoned astronomers but to casual skywatchers, children, people living in cities, anyone who looks up. Unlike a supernova, which can fade in days or weeks, this nova is expected to linger. After the initial outburst, V Sagittae's brightness will slowly decline over the course of several weeks. During that time, the expanding gas shell will radiate in multiple wavelengths: visible light, ultraviolet, and possibly even X-rays, allowing astronomers to study its structure, composition, and velocity. Specialized telescopes will examine its spectrum to determine what elements were created or ejected in the explosion, offering insight into the complex nuclear processes that took place on the white dwarf's surface. The power of this nova will not just be visual, it will be scientific. This is an opportunity for humanity to test everything we think we know about mass transfer, accretion physics, and stellar eruptions. With coordinated global monitoring campaigns already in planning stages, observatories around the world will track the explosion from every possible angle and wavelength. Space telescopes like the James Webb Space Telescope and Hubble, assuming they're still operational or succeeded by newer instruments, will likely turn their gaze towards Sagitta to watch the drama unfold in exquisite detail. Radio telescopes will map the expanding gas shell, detecting the shockwaves as they crash into the surrounding interstellar medium. Infrared telescopes will look for signs of dust formation, as cooling gases condense into microscopic particles that may one day seed star-forming regions. Even amateur astronomers will contribute, capturing light curves and images that, when added to the broader scientific dataset, may help refine our models of nova behavior. All of this, from professional observatories to backyard telescopes, is possible because of one fact: the white dwarf survives. It doesn't die. It continues. And that continuity provides a long window of time for observation, tracking, and discovery. In the violent world of stellar explosions, that's a rare luxury. But even without the total annihilation of the white dwarf, the impact of the nova will be profound, on both science and culture. Most people alive today have never witnessed a true nova, especially one this bright. While smaller, fainter novae occur almost every year in distant parts of the Milky Way, they're often invisible without telescopic aid. V Sagittae will change that. It will bring a nova into the public consciousness in a way few stellar events ever have. It will become a talking point across the globe, a new star, suddenly appearing where none was visible before. It will also challenge our perception of the night sky. For weeks, constellations will look different. Old star charts will appear outdated. Sagitta, once a faint, overlooked patch of sky, will become a radiant beacon. Children will grow up remembering the time the sky lit up. And in the quiet hours of the night, people will step outside, tilt their heads back, and feel something ancient stir, a primal awe that humans have felt for millennia when the heavens suddenly change. So yes, this nova is not a supernova. It will not destroy the white dwarf, or send gamma rays flooding toward Earth. It will not tear space-time or collapse into a black hole. But it will shine. It will burn brighter than anything we've seen from a star in generations. It will announce itself in no uncertain terms. And for those of us watching from Earth, it will be more than powerful enough. It will be unforgettable. The brightness of V Sagittae's coming eruption isn't just a scientific curiosity. It's a cosmic spectacle waiting to unfold. Astronomers estimate that during the peak of its nova outburst, V Sagittae could reach an apparent magnitude of -2 or brighter. But what does that really mean? How bright is -2 magnitude in the grand scale of the night sky? To answer that, we must take a closer look at how we measure celestial brightness, and then place V Sagittae within that luminous hierarchy. In astronomy, brightness is measured on a scale known as apparent magnitude. This system, originally developed by the ancient Greek astronomer Hipparchus, assigns lower numbers to brighter objects, with the brightest visible things having negative values. For reference, here are a few notable magnitude benchmarks. The full moon is about -12.7. Venus at its peak brilliance can reach around -4.7. Jupiter hovers between -2.0 and -2.9. Sirius, the brightest star in the night sky, is about -1.46. The faintest stars visible to the naked eye under ideal dark skies are around +6. So if V Sagittae truly reaches -2 magnitude, or potentially even brighter, it would outshine Sirius, surpass Jupiter during some periods, and even begin to approach the brilliance of Venus, which is regularly mistaken for a UFO due to its striking visibility. At that level of magnitude, the nova wouldn't just be visible, it would be unmissable. Under dark skies, V Sagittae would become the dominant object in its corner of the sky. It would draw the eyes of everyone, from seasoned astronomers to casual stargazers. People unfamiliar with celestial events would step outside and immediately notice something strange, something new, a piercing light in the constellation of Sagitta where once there had been only faint stars. The difference will be so dramatic that even those living in light-polluted cities, who rarely see more than a few dozen stars, will be able to spot it with ease. And if the nova reaches the more optimistic estimates, around magnitude -4, it could rival Venus, making it not just visible at night, but potentially during the day. Daylight visibility of celestial objects is extremely rare. The moon and sun are always visible, of course, but outside of solar eclipses, only the brightest planets can sometimes be seen in full daylight, and only under favorable conditions. For a nova to shine with such power that it could be spotted during daylight hours would be unprecedented in modern times. To witness a new light appear in the sky bright enough to challenge the natural luminaries would be both disorienting and deeply awe-inspiring. Imagine looking up at noon and seeing a pinpoint of light glowing faintly beside the sun, refusing to be washed out by blue sky and sunlight. It would feel almost supernatural, except we would know precisely what caused it, and how long we've waited to see it. At night, the nova will completely change the appearance of the constellation Sagitta. Sagitta is a small and faint grouping of stars shaped like an arrow, barely noticeable under typical viewing conditions. But once V Sagittae erupts, it will blaze like a jewel at its center. The star will temporarily become the brightest point in that region of the sky, illuminating not just its surroundings, but our entire perception of that section of the Milky Way. In some ways, V Sagittae's brightness will distort our sense of the heavens. Star charts will be rendered temporarily inaccurate. Constellations won't look the same. The sudden brightness will act like a lighthouse beam in what was once a quiet, unremarkable part of the sky. And while the exact magnitude it will achieve is still uncertain, dependent on variables like the amount of material expelled, the rate of nuclear burning, and the final size of the outburst, most predictions agree, this will be the brightest nova seen in centuries. To get a sense of historical comparison, consider the nova of 1572, observed by Tycho Brahe, which reached a magnitude of about -4 and was visible in daylight for over 2 weeks. At the time, it was revolutionary. It helped overturn the prevailing belief that the heavens were immutable. Tycho's nova proved that change does occur in the heavens. Likewise, the nova of 1918 in the constellation Aquila reached magnitude -1.4 and was visible for over a month. These events are incredibly rare, and V Sagittae is poised to match or exceed them. Brightness, of course, is only one part of the experience. But it is the most immediate. It's what people will see first. It's what will dominate photographs, headlines, and conversations around the globe. For many, it will be their first direct, unfiltered encounter with a dramatic event in deep space. And because the nova's brightness will unfold over days and linger for weeks, it will become a shared global experience, something people return to night after night, watching as it slowly fades and knowing that they were witnesses to a cosmic turning point. The beauty of brightness is also that it transcends education or equipment. You don't need a telescope. You don't need a degree. You don't even need to know the name, V Sagittae. All you need is to look up and see it. That accessibility is what makes this event so culturally significant. It will be talked about by scientists and skywatchers, yes, but also by children, journalists, artists, and poets. The brightness of V Sagittae will inspire, astonish, and perhaps even unsettle. It will remind us how alive and unpredictable our universe is. It will remind us that the stars are not eternal beacons, but actors on a stage of physics and time, each with their own entrance, exit, and moment in the spotlight. So how bright will it be? Bright enough to change the sky. Bright enough to be seen by millions. Bright enough to leave a memory that outlasts the light itself. When V Sagittae finally erupts, it will not be a fleeting flash or a blink and you miss it phenomenon. This is not a shooting star burning out in seconds or a meteor slicing across the sky in a heartbeat. V Sagittae's nova will unfold over time, evolving before our eyes, and it will linger, making it one of the rare celestial events that gives the human race the luxury of time to watch, to study, to marvel. According to astronomers and the models that forecast these events, the visible eruption of V Sagittae could last several weeks, possibly even stretching toward a couple of months, depending on how much material is ejected, how quickly it disperses, and how the explosion plays out. This is remarkably long for such a high-energy burst of light and matter, and it's one of the aspects that makes this particular nova so captivating. The event will likely begin with a rapid ascent to peak brightness. Once the critical mass of accreted hydrogen ignites in a runaway thermonuclear explosion on the surface of the white dwarf, the system will flare to life within hours or days. During this rise to maximum light, the brightness will increase dramatically, following a steep curve until it reaches its peak magnitude, possibly -2 or brighter, as previously discussed. At this point, V Sagittae will be at its most luminous, clearly visible to the naked eye and potentially even during daylight hours. This peak may last for a few days, during which the nova will dominate the night sky, become a global sensation, and stir fascination around the world. People in all corners of the Earth, regardless of latitude or culture, will be able to witness it, a glowing reminder of our shared place under the same stars. But unlike transient cosmic flashes, the story won't end there. After reaching its brightest phase, V Sagittae's nova will enter the decline stage, where its brightness begins to gradually diminish. This is a critical phase from an astronomical standpoint because it allows scientists to study the mechanics of the eruption in real time. By tracking the light curve, the plot of brightness over time, researchers can gain insights into the ejected material, the energy of the explosion, and how quickly the nova's gases expand and cool. In many novae, the rate of decline is directly related to the speed and amount of material ejected. Fast novae fade rapidly over days or a couple of weeks, while slow novae take much longer, potentially remaining visible for a month or more. V Sagittae's unique configuration, its extreme mass transfer, its high-energy state, and its unprecedented brightness, suggests that it may behave more like a slow nova in terms of visibility duration. A longer decline period also allows for a broader window of observation from both ground and space-based telescopes. During this phase, astronomers will monitor changes in the nova's spectrum, the breakdown of light into its component colors. These spectral shifts will reveal how the composition of the ejected gas changes over time, how it interacts with surrounding interstellar material, and how the white dwarf begins to settle after the detonation. The expanding shell of ionized gas, once it cools and begins to slow, might form a visible nebula or remnant, which could become a target of interest for astronomers for years to come. For the casual observer, this slow fade will be a rare invitation to watch a real-time transformation in the sky. One night, the nova may be brighter than all stars around it. A week later, it will be noticeably dimmer. Another week, and it may resemble a modest first-magnitude star. Then a third week, perhaps fading to second or third magnitude, still visible, but no longer as overwhelming. And then eventually, sometime in the following weeks, it will dip below naked eye visibility, fading into the background noise of the cosmos, invisible without telescopes. But the memory of it will remain. That's the paradox of such events. Though the light eventually fades, the impression it leaves is permanent. People will remember where they were when they first saw the strange new star in the sky. Photos will be taken. News segments will be aired. Time-lapse videos will capture its decline frame by frame. And long after the nova disappears from casual view, astronomers will continue to observe the remnants for decades, perhaps centuries, building a long-term record of the aftermath. It's also worth noting that while the naked eye visibility may last for weeks, the nova's aftereffects could persist in other wavelengths of light, especially in ultraviolet and radio, for much longer. Infrared telescopes may detect cooling gas and dust that form in the wake of the explosion. Radio observatories may listen to the echo of shockwaves traveling through the interstellar medium. In this way, even though the brilliant visual moment fades, the nova remains alive in the instruments and data of our global scientific community. For people watching from Earth, the slow fade will feel almost like a sunset that takes weeks to complete, a celestial bloom opening and then slowly closing. In a world where news cycles move in hours and trends disappear in days, the enduring presence of V Sagittae's light will stand apart. It will become something people return to night after night, marking its gradual disappearance like the closing of a chapter in the story of the universe. And when the light does fade below visibility, when V Sagittae becomes again what it once was, a faint, unassuming star in a quiet corner of the constellation Sagitta, its eruption will still echo. In the data, in the images, in the minds of those who watched it unfold. It will have changed not just the sky, but our understanding of time, light, and the delicate violence of stars. So, how long will it last? Long enough for the world to look up in wonder. Long enough to remind us that stars, even in death, take their time to say goodbye. One of the most extraordinary aspects of the V Sagittae nova is its proximity, not in the sense that it's right next door, but in cosmic terms, it's close enough to make a world of difference. most of the dramatic and violent events in the universe, gamma-ray bursts, black hole mergers, supernovae, happen so far away that we require powerful telescopes just to detect their signals, let alone see them with our own eyes. But V Sagittae breaks that mold. It's near enough, relatively speaking, that when it erupts, you won't need a telescope, binoculars, or even dark skies. Just your eyes. Just a place to look up. That makes it one of the rarest kinds of celestial events, a front row seat to a stellar explosion. Located roughly 7,800 light-years away in the constellation Sagitta, V Sagittae sits well within the Milky Way galaxy. It's not in some distant neighboring galaxy millions of light-years out. It's in our cosmic backyard. That might not sound close. After all, light takes nearly 8 millennia to reach us from there. But when you consider the scale of the universe, it's a stone's throw. Some of the most famous supernovae we've observed have occurred in other galaxies, far beyond our reach for any kind of naked-eye visibility. But V Sagittae will be different. It will be visible to everyone on Earth, simply by looking toward the right part of the sky. This nearness allows something magical to happen. The explosion, powerful as it is, doesn't have to compete with billions of light-years of cosmic fog. It doesn't have to scream across intergalactic voids just to reach us. The light from V Sagittae will come directly, unfiltered and blazing, magnitudes brighter than it was just the night before. You'll walk outside, glance upward, and where once there was darkness, or perhaps a dim speck invisible to the unaided eye, there will be a star so brilliant it might cast shadows under the right conditions. And the best part? Everyone can witness it. This isn't a privilege reserved for astronomers. You won't need to be on a remote mountain top, away from civilization, with $1,000 telescope. You won't need to be anywhere special at all. Whether you're in a city, a suburb, or a rural village, whether you're on one side of the planet or the other, the nova will be there, waiting to be seen. The entire planet will, for a short time, share the same night light in the sky. This makes V Sagittae an especially human event. The experience won't be mediated by machines, data, or infrared wavelengths only decipherable by software. It will be visceral. You'll feel it. Just as ancient humans stared up in awe at the mysterious flares and new stars of their time. And because it will be visible for weeks, the experience will be ongoing. It won't be a brief flash, missed by most and forgotten quickly. Instead, it will become part of the rhythm of the evening sky. Night after night, people will step outside and check to see if it's still there. Friends will point it out to each other. Kids will ask what it is. People will take pictures, create time-lapse, start conversations online, and write articles. It will become a fixture, if only for a time, a temporary neighbor, reminding us that the stars above are not static, not cold, not distant, but alive and ever-changing. There's a strange intimacy that comes with seeing something so vast unfold with your own eyes. When we watch a meteor streak across the sky, we're seeing a fragment of rock burn up in our own atmosphere. When we watch a solar eclipse, we're witnessing a dance between the Earth, Moon, and Sun, a local affair. But with V Sagittae, we will see the light from a thermonuclear explosion that happened 7,800 years ago, just now arriving at our skies. That means when you look at the nova, you're not just seeing a star explode, you're seeing a moment of history, a frozen flash from the past illuminating your present. It's almost poetic. By the time we see the nova with our eyes, the explosion will have long since happened. The gas will have long since expanded, cooled, and drifted outward in all directions. The light, like a messenger from an ancient war, will just be arriving, carrying news of what once was. That's the bittersweet beauty of stargazing. You're always seeing the past. But in the case of V Sagittae, you're also watching the future you were promised, a predicted event come to pass, seen by generations who waited for it. And make no mistake, this front row seat is incredibly rare. Very few events in astronomy offer the ability to both predict and experience them with the naked eye. Comets come and go, eclipses follow a calculable rhythm, and planets perform their slow celestial ballet across the heavens. But a nova? One this close, this bright, and this precisely predicted? That's nearly unheard of. To be alive during the eruption of V Sagittae is to be part of a chosen generation. Future historians, scientists, and skywatchers will look back on the data we collect, the images we capture, and the stories we tell about this event. They'll ask, what did it look like? How bright did it get? Where were you when you saw it for the first time? Because the truth is, most stars will live and die without anyone ever knowing they existed. The universe is vast and quiet. But this one, this star system, we know. We see it coming. We're watching it tighten its orbit, increase in brightness, speed toward critical mass. And one day, that slow tension will snap, and the sky will bloom. So when that happens, take a moment. Step outside. Look up. Because not many people in human history have had the chance to witness the death cry of a star system, live and unfiltered. But you will. From right here. On Earth. Finding V Sagittae in the sky today isn't easy. In its current state, it's an unassuming and relatively faint star tucked away in one of the smallest constellations in the northern sky, Sagitta, meaning the arrow, in Latin. Unlike the bold outlines of Orion or the easily recognizable dipper shapes of Ursa Major and Ursa Minor, Sagitta is often overlooked by casual stargazers. It's a subtle arrow-shaped asterism situated between the brighter constellations of Aquila, the Eagle, and Vulpecula, the little fox, nestled along the dense plain of the Milky Way. Sagitta is the third smallest constellation in the entire sky, covering less than 80 square degrees, smaller than some well-known deep-sky objects like the Andromeda Galaxy. But what it lacks in size, it makes up for in celestial importance. That's because somewhere within its modest outline lies the ticking time bomb we call V Sagittae. Right now, V Sagittae is classified as a variable star. Its brightness fluctuates over time, and even at its brightest, it's still below naked eye visibility, hovering around 15th magnitude in most observations. For amateur astronomers with telescopes, it appears as an undistinguished point of light in a crowded star field, easy to miss without precise coordinates. It's only thanks to detailed star charts and modern astrophotography that we're able to pinpoint it at all. But come the mid-2080s, all of that will change. Once the nova event occurs, V Sagittae will dominate not just Sagitta, but the entire region of the sky around it. It will transform this quiet patch of celestial real estate into a center of attention, drawing eyes that have never before paused on the constellation. What was once dim and distant will become a beacon, causing many to discover the constellation Sagitta for the first time, by accident, simply because that's where the light explodes. But for those curious now, for those who want to find it before the detonation, it's possible, though it requires patience. Sagitta is best viewed in the summer months in the northern hemisphere, particularly in July and August, when it reaches its highest point in the night sky. Around midnight during this time, look toward the southern sky to locate the bright star Altair, which marks the head of Aquila. Sagitta lies just a bit north of Altair, nestled between Delphinus, the dolphin, and Vulpecula. You won't find any especially bright stars here. Sagitta's four main stars form a narrow, almost perfect arrow shape pointing westward, but once you've found that asterism, you've found the neighborhood. To locate V Sagittae precisely, astronomers use right ascension and declination, the celestial equivalent of longitude and latitude. Its coordinates are approximately: right ascension, 19 hours 18 minutes and 52.0 seconds. Declination, plus 18 degrees 42 minutes 53. These numbers place it squarely within the band of the Milky Way, amidst a rich background of stars, dust, and nebulae. This location is not just picturesque, it's scientifically valuable. The region of the Milky Way that Sagitta cuts across is dense with interstellar material, and when the nova erupts, that material could light up in spectacular ways. The shockwaves and radiation from the explosion may interact with nearby gas clouds, possibly creating a glowing halo or remnant nebula that persists long after the initial flash fades. Its galactic address, roughly 7,800 light-years away, places it well within the inner regions of our Milky Way. While this distance is too great for the nova to pose any physical threat to Earth, it's close enough for the explosion to be incredibly luminous. For comparison, the Crab supernova, SN 1054, which created the Crab Nebula and was visible during the day in 1054 AD, occurred around 6,500 light-years away. V Sagittae is only a bit farther, and while not a supernova, its eruption will be powerful enough to achieve a similar level of visibility. And because it lies within the plane of the Milky Way, the backdrop against which we'll see this nova will be breathtaking. The galactic plane, especially visible in summer from dark sky locations, is filled with glowing clouds of gas and dense clusters of stars. When V Sagittae erupts, it won't blaze alone in a blank sky. It will glow against the brilliant tapestry of the Milky Way's core, giving photographers and astronomers an unforgettable target. Beyond its location in the sky, V Sagittae's position within the larger galactic structure also holds significance. It sits among a class of binary systems that are found in relatively young regions of the galaxy, areas where star formation is still active. This hints at its possible origin story, suggesting that its components were likely born from one of the many stellar nurseries that have shaped this part of the Milky Way over the last few 100 million years. From that origin, the system evolved. The larger star eventually began transferring mass to its smaller, denser white dwarf companion, starting a deadly spiral that will now culminate in a nova unlike any other we've seen in recent times. And this entire saga, millions of years in the making, will reach its climax right in the heart of this otherwise unremarkable constellation. In the years leading up to the eruption, stargazers will start to take a renewed interest in Sagitta. It will become a training ground for amateur astronomers eager to watch the pre-nova stages unfold. People will begin pointing their telescopes toward this patch of sky regularly, just to get a glimpse, however faint, of the ticking time bomb. And when it finally happens, the small, quiet arrow in the sky will have made its mark on history. So while Sagitta may not yet have the fame of Orion, Scorpius, or the Big Dipper, that will change. V Sagittae will put it on the map. Forever. In the heart of the V Sagittae system, a deadly dance unfolds, a gravitational embrace so tight, so intimate, and so volatile that it will eventually trigger a thermonuclear eruption visible across the Earth's sky. This dance isn't between a single star and its distant planet, nor is it a slow celestial drift. It's an urgent, chaotic spiral between two stars locked in a destructive waltz that repeats itself every 12.3 hours. That's right. Every half-day, the two stellar bodies in V Sagittae complete a full orbit around one another. That's less time than it takes Earth to rotate once on its axis. You could wake up, go to work, eat lunch, and by the time you returned home, the stars would have circled each other entirely. In astronomical terms, that's incredibly fast. And it tells us just how close together these two objects really are. The primary components of this binary system are a white dwarf and a main sequence star, the latter being somewhat similar to our Sun but currently bloated and unstable due to the intense gravitational influence of its companion. The white dwarf, on the other hand, is a stellar corpse, a remnant of a star that has already exhausted its fuel, collapsed inward, and now sits as a superdense object with a mass comparable to the Sun crammed into a sphere about the size of Earth. Because the white dwarf is so compact, its gravitational pull is immense. As the two orbit each other, tidal forces stretch and deform the companion star, pulling material off its outer layers and spiraling it toward the white dwarf in a chaotic, spiraling stream. This process is known as Roche-Lobe overflow, and in V Sagittae, it's happening at one of the fastest known rates among any such systems. Matter flows continuously, building up on the white dwarf's surface and creating an unstable, growing envelope of hydrogen gas, fuel for the eventual nova. Now, the key to this system's dangerous future lies in that orbital period. A 12.3-hour orbit implies extreme proximity. We're talking about a separation of just a few million kilometers, closer than the distance from Earth to the Moon. These stars are not just companions, they're on the verge of fusion. Their gravitational forces are not only stealing mass from one another, they're warping space-time around them. And every second, that orbit tightens. This shrinking orbit is a product of what's known as gravitational radiation, a slow but steady loss of orbital energy due to the emission of gravitational waves. While these waves are extraordinarily weak in this context, far beyond our ability to detect from such a distant source, their cumulative effect is significant. Over time, they cause the orbit to decay. And as the stars draw closer, the mass transfer accelerates. This is the dangerous feedback loop at the core of V Sagittae's story. Closer orbit leads to more mass transfer, which destabilizes the system further, tightening the orbit even more. Think of it as a cosmic whirlpool. Two stars circling each other faster and faster, closer and closer, drawn into each other's gravitational well. The tighter they spiral, the more energy is released. The system becomes more luminous. The white dwarf accumulates more stolen mass, inching toward the point where a thermonuclear chain reaction will ignite across its surface. Not a supernova, but still a cataclysm, a nova bright enough to cast shadows on Earth. Astronomers have observed that over the last few decades, the rate of orbital decay in V Sagittae has been increasing. That's one of the most critical clues suggesting a nova is imminent. In fact, this accelerating orbital collapse was a key piece of evidence that helped researchers predict the nova's likely timeframe, around 2083, give or take a few years. We are watching this system wind itself up, like a clock approaching midnight. And unlike many other variable stars or potential nova candidates, V Sagittae gives us a concrete, visible marker of its instability, its rapidly decreasing orbital period. Every orbit tightens the tension between the two stars. Every pass pulls more mass, increases pressure, and adds to the invisible countdown happening deep inside the white dwarf's growing hydrogen envelope. This isn't just a random process, it's a meticulously choreographed death spiral. A cosmic ballet, where the choreography ends in explosion. The motion of the two stars also creates an accretion disk around the white dwarf, a glowing, swirling halo of stolen material gradually funneling inward. This disk is a hotbed of magnetic chaos and high-energy physics. Friction in the disk causes heating, which in turn emits light in various wavelengths, including X-rays and ultraviolet. The flickering we observe in V Sagittae's light curve, those subtle pulses and variations over time, are influenced by this disk, by the exact angles of orbit, and by the flows of matter between the two bodies. And this is what makes binary systems like V Sagittae so fascinating. They're not static. They're alive with motion. They pulse, shift, change, and evolve, not over millions of years, but over decades, years, even days. The nova isn't just a future event. The build-up is happening now. The dance is ongoing. When we observe V Sagittae today, we're not just seeing a distant star. We're watching a dangerous waltz from 7,800 light-years away. We're witnessing the gravitational mechanics of two stars in collision, in a tango of attraction and destruction. And we know the end of this dance. We've done the math. We've seen the pattern. The choreography is clear, and the final act is approaching fast. By the time the orbit tightens to its limit, by the time the white dwarf's stolen fuel reaches the critical pressure, by the time the temperature spikes to ignition, there will be no stopping it. The dance will end in fire, and the night will blaze with its farewell. In the heart of the V Sagittae system, a strange and asymmetric relationship dominates, a paradoxical game of gravitational theft in which the smaller, denser object is the more powerful player. Here, the white dwarf, a stellar corpse no larger than Earth, commands the fate of its far larger but far less dense companion. And it does so by engaging in a relentless act of mass transfer, stealing hydrogen-rich material in a quiet yet persistent act of celestial cannibalism. The white dwarf's intense gravitational field is the key to this process. Although it has a radius only about the size of our planet, its mass is close to that of the Sun. This means its surface gravity is hundreds of thousands of times stronger than Earth's, capable of pulling and distorting anything nearby, including the outer layers of its stellar companion. The result is a bridge of matter, an invisible stream of hydrogen gas, flowing from the companion star to the white dwarf. This phenomenon, known as Roche lobe overflow, marks the beginning of a process that will ultimately lead to the system's violent detonation. The donor star, while larger in size, is weakened by its bloated, unstable structure. It's being stretched and distorted, teetering on the edge of its gravitational boundaries. Its material flows through the inner Lagrangian point, the point between the two stars where gravitational forces balance, and falls onto the white dwarf's accretion disk, a swirling ring of hot plasma spinning ever faster as it spirals inward. What makes V Sagittae so exceptional is the rate at which this mass transfer is happening. In typical cataclysmic variable systems, mass transfer occurs slowly, with the white dwarf accreting enough material over decades or centuries to trigger an occasional nova. But V Sagittae doesn't play by those rules. It's transferring matter at one of the highest rates ever observed for a binary star of its type, estimated to be more than 10 solar masses per year. That might sound minuscule, but in astrophysical terms, it's like a fire hose of stellar gas pouring from one star to another. This high rate of accretion is one of the strongest indicators that V Sagittae is not just unusual, it's on the brink. The faster the white dwarf pulls a material, the more rapidly it approaches a critical mass of hydrogen on its surface. Once this material builds up to the ignition point, the pressure and temperature will reach levels that cause the hydrogen to undergo runaway fusion, releasing a massive burst of energy and ejecting the surface layers in a brilliant explosion, a nova. But what happens in the meantime is just as fascinating. As material spirals inward, it heats to extreme temperatures, millions of degrees in some cases, causing the accretion disk to glow in ultraviolet and X-ray wavelengths. This makes V Sagittae an intriguing target not just for optical telescopes, but also for observatories that scan the sky in higher energy bands. By watching the flickering emissions from the accretion disk, astronomers can measure the exact flow of material and monitor the system's ever-growing instability. The stolen mass doesn't simply disappear in the nova explosion either. Some of it will be ejected back into space, forming a shell of expanding gas. But the core of the white dwarf remains scarred but intact, potentially ready to begin the cycle anew. However, in the case of V Sagittae, the violence of the outburst, and the uniquely extreme mass transfer, suggests the system might evolve beyond this point. It may not merely go nova once. It may merge entirely in a future stage, possibly even culminating in a Type I supernova if the white dwarf reaches the Chandrasekhar limit of about 1.4 solar masses. For now, though, what we're witnessing is a dangerous balancing act, a cosmic game of accumulation and delay. The white dwarf is like a thief gathering stolen treasure too quickly, hoarding more than it can safely store. And every gram of matter it adds to its surface brings it closer to a catastrophic flashpoint. But mass transfer is not a smooth process. It's chaotic, turbulent, and riddled with feedback loops. The more material is transferred, the more distorted the donor star becomes. This in turn leads to increased transfer rates, which amplify the instability. Some models suggest the donor star may eventually be completely stripped of its outer layers, reduced to a degenerate core itself, creating an exotic and even more volatile binary pairing. In such a case, the roles could invert again, or the two stars could merge entirely, sending the system hurtling toward a more violent fate. It's this high-speed, high-volume mass transfer that makes V Sagittae's timeline so dramatic. Other binary systems can linger in quasi-stable states for millennia, undergoing occasional minor eruptions but otherwise remaining relatively quiet. V Sagittae, on the other hand, is like a dam under pressure. It's accumulating matter too fast to maintain equilibrium, and when it breaks, the outburst will be monumental. One of the reasons we can predict the eruption with such relative confidence is because of how precisely we can monitor this mass transfer. The system's brightness is increasing exponentially, and this is directly correlated to the rate at which matter is being added to the white dwarf. This exponential rise isn't subtle. It's been accelerating measurably over recent decades, and models show this kind of growth always precedes detonation in similar systems, just not usually at this scale. In other words, the mass transfer game is nearing its endgame. The white dwarf is almost full. The fuel tank is nearly at capacity. And when it overflows, not with gasoline but with hydrogen, not in a spark but in a thermonuclear fireball, the night sky will light up with the fury of stars at war. We are watching this theft in progress. And the price of that stolen mass will be paid in light. Each day, each orbit, each flicker of light from the V Sagittae system is a tick in a celestial countdown. This is not a metaphor. This is an actual ticking clock written into the physics of stars and gravity, a countdown that ends not in silence but in eruption. V Sagittae is nearing the final phase of its turbulent life, not a slow fade into stellar old age, but a swift, climactic outburst that will change the sky. The clock is ticking, and we are close enough in both time and distance to witness the finale. The key to this ticking clock is the increasing rate of mass transfer between the donor star and the white dwarf. As discussed earlier, the smaller white dwarf is pulling hydrogen-rich gas from its bloated companion at an extraordinary rate. But this isn't a stable or benign exchange. The process is feeding an accelerating cycle. More mass means more gravitational binding, which leads to more intense accretion, which leads to even more mass loss from the donor star. This is what astronomers call a positive feedback loop, and it is notoriously unstable. It's like pouring gasoline on a fire. The more you feed it, the more uncontrollable it becomes. In V Sagittae's case, this feedback loop is now at a dangerous stage. Observations show that its overall brightness has been increasing exponentially. This isn't random variability. This is a measured, calculable upward curve, one that scientists can plot and extrapolate. And when they do, all models point to the same general time frame, around the year 2083. That's when the brightness and mass transfer reach the tipping point, the moment when the hydrogen accumulated on the white dwarf's surface reaches critical mass and ignites in a thermonuclear flash. It's worth pausing here to appreciate the magnitude of what this means. In astronomy, most events are either too far in the past or too far in the future to touch. The universe moves on million-year timescales. Even supernovae, when they happen, tend to be random and far away. But V Sagittae is a rare exception. We are living not just within the era of its transformation, we are living within decades of it. We've been able to watch it grow brighter in real time, to observe changes in its spectrum, and to measure the shift in its orbital timing. And with those measurements, we've essentially set a cosmic alarm clock. That alarm is approaching fast. And while the exact year might be off by a few, nova predictions are inherently probabilistic. The trend is undeniable. The system is nearing a critical instability. The current models show that if the acceleration of brightness continues along the curve we've observed, V Sagittae will undergo its nova outburst in the mid-2080s, give or take a few years. This puts today's astronomers in a unique position. They're not just watching a star, they're anticipating it. Observatories across the globe and in orbit are increasingly pointing their instruments towards Sagitta, gathering light curves, radial velocity measurements, and spectral data. Every tiny fluctuation matters. Every unexpected variation could be the signal of something new, a shift in the accretion disk, a mass ejection event, or the first sparks of ignition. The system is becoming not just a subject of study, but a laboratory of stellar death, where we can watch the end stages unfold in slow motion. There's something strangely intimate about this process. We're not just learning about V Sagittae. We're watching it die, predictably, measurably, and in real time. And in doing so, we're witnessing something incredibly rare, a moment when the universe lets us in on its secrets before they happen. It's as if we've been handed the final pages of a book while the middle chapters are still playing out before us. But there's more to this ticking clock than science alone. The knowledge of its impending explosion has rippled beyond academic circles. News articles, documentaries, YouTube channels, and stargazing communities have begun to take notice. V Sagittae has become a story of human curiosity as much as stellar evolution. It's a countdown that we can all share. A future date when something ancient and vast will briefly break into our everyday lives and remind us that we are part of a living, changing cosmos. Even now, classrooms discuss the 2083 prediction. Children born today will likely see the nova as young adults or middle-aged observers. Astronomers nearing retirement today are training the next generation to continue monitoring the system. In many ways, V Sagittae is becoming a legacy project, a star passed down between generations, like Halley's Comet, but far more explosive. And unlike many cosmic events, the science behind this ticking clock is clear. We know the mass of the white dwarf. We know the orbital period. We've measured the accretion rate. We've modeled the transfer of energy. And though there are still uncertainties, the convergence of data gives us remarkable confidence in what's coming. The only thing left is time, and we know exactly how little of it remains. But there is another element to consider. The ticking clock doesn't just point to the moment of eruption, it also tells us something profound about how stars evolve, how they end, and how their violence seeds the galaxy with the elements that make up everything from planets to people. In the seconds before the nova, deep within the accreted hydrogen layer, temperatures will soar to tens of millions of degrees. Fusion will ignite. The outer layers of the white dwarf will be blown outward at supersonic speeds. And with that, new elements will be hurled into space, enriching the interstellar medium with fresh material for future generations of stars. The end of V Sagittae is also a beginning. Its clock is not just ticking toward death, but toward transformation, a flash that will light the skies and rewrite our maps. A single moment that connects stellar physics, human history, and cosmic evolution. We don't need to wonder if it will happen. We only need to wait and watch. In the field of astronomy, where time is measured in eons and changes often unfold over millions of years, exponential change is a red flag. When astronomers speak of a star's brightness increasing exponentially, it signals something urgent, unstable, and often catastrophic. And that's exactly what we're witnessing with V Sagittae, a steady but rapidly escalating rise in brightness that suggests the system is on the verge of a colossal transformation. It's not a theory or a vague guess. This change is measurable, tracked with precision instruments over the course of decades. And the results point clearly to a system in its final, volatile phase. Let's break this down. The concept of a brightness curve is simple in principle. Astronomers monitor how much light a celestial object emits over time. This can be done using photometry, a technique that measures a star's magnitude, essentially its visual brightness as observed from Earth. When plotted over time, a stable star shows only minor fluctuations. A variable star might rise and fall cyclically. But V Sagittae is different. When its brightness curve is plotted over the last century, the trend is not linear, it is exponential. Each year, the star grows not just brighter, but brighter at a faster rate than the year before. This is no coincidence. The light we're seeing is the outward expression of intense internal processes, namely the runaway mass transfer from the companion star to the white dwarf. As the white dwarf pulls more gas from its neighbor, the accretion disk surrounding it glows ever hotter. More material spirals inward, more gravitational energy is converted into heat and light, and the overall system emits more radiation across the spectrum, especially in the visible and ultraviolet bands. If you were to graph this brightness increase on a chart, it wouldn't form a straight incline, it would form a curve that steepens sharply toward the present, like the rising edge of a tidal wave. And that curve is one of the most important predictive tools astronomers have in forecasting the coming nova. The math behind exponential curves tells us that once such a process begins, the system won't gradually stabilize. Instead, it will continue accelerating until it crashes. This exponential brightening has been confirmed by both ground-based telescopes and long-term sky surveys. Instruments like the All-Sky Automated Survey ASUS Gaia and others have provided increasingly detailed data points. When compiled, they show a startling reality. V Sagittae has increased in brightness by a factor of over 10 in just the last century. And in astrophysical terms, that's blindingly fast. By extrapolating this trend forward, astronomers have confidently estimated that V Sagittae will reach nova conditions by around the year 2083, give or take a decade depending on precise modeling. Importantly, this brightness increase isn't merely a passive glow, it's a visible signature of instability. Stars typically shine with incredible consistency, powered by the fusion of hydrogen into helium in their cores. But in V Sagittae's case, the growing luminosity isn't coming from fusion in the white dwarf's interior. It's coming from the accreted material and the gravitational friction within the accretion disk. This light is chaotic, unstable, and unsustainable. It's the light of a star system on the edge of collapse. There's also another aspect to consider: flickering. As the mass transfer intensifies, astronomers have noted increased fluctuations, rapid, chaotic changes in brightness on short timescales. These aren't random. They're tied to the flow of gas between the two stars, the turbulence in the accretion disk, and the buildup of material on the white dwarf's surface. This flickering, combined with the exponential long-term rise, tells us that the entire system is entering a critical phase where minor changes can trigger major consequences. To put this into perspective, if this trend continues, the brightness of V Sagittae may soon become detectable by amateur astronomers with small telescopes. Eventually, it will reach the point where even binoculars can pick it out from the background stars of Sagitta. And after that, once the final phase begins, it will rise past the limits of human detection into visibility with the naked eye, first as a faint point, then a bright one, and finally as a luminous beacon outshining all stars save the sun. But here's the deeper meaning behind the brightness curve. It's not just about predicting a nova. It's about understanding the dynamic, ever-changing nature of stellar evolution. V Sagittae has evolved from a quiet, overlooked binary system into one of the most closely watched stars in the sky. Its curve tells a story not of gradual aging, but of cosmic urgency, of a star system rushing headlong into a future it cannot escape. This is why astronomers are so fascinated with the curve. It's a kind of heartbeat, a pulse that speeds up as the climax approaches. And that curve is also a warning. It says, the system is no longer stable. The balance has been broken. The transfer of mass has passed the threshold of moderation. The physics of stellar death are now in motion, and the eruption is not a question of if, but when. The exponential brightness curve of V Sagittae is, in essence, a countdown clock written in light, a smooth, upward arc that will soon break into a burst of brilliance. That moment, when the curve reaches its final crescendo, will be unlike anything we've seen in modern history. A nova, yes, but one so anticipated, so modeled, so perfectly tracked that humanity will be waiting for it with cameras ready, with satellites poised, with eyes turned skyward. And when that day comes, it will not be sudden for those who've followed the curve. It will be the final tick in a pattern we've watched unfold for generations, a flash foretold in graphs, in algorithms, and in the slow, exponential rise of light from a star that refuses to go quietly. When V Sagittae was first catalogued in 1902, it didn't raise any alarms. At that time, it was simply noted as a variable star, meaning its brightness fluctuated over time, a fairly common trait. The Milky Way is filled with stars that pulse, flicker, or vary in brightness for any number of reasons, some because of surface pulsations, others because of eclipsing binary companions, and still others due to dust or magnetic cycles. V Sagittae, at first glance, seemed to fit comfortably into this category, an ordinary member of a vast class of stars. In the early 20th century, our understanding of stellar variability was still developing. The idea that stars could brighten and dim over predictable or unpredictable intervals was known, but the underlying physics wasn't always clear. Instruments were limited. Observations were slower, and long-term data was sparse. So when V Sagittae was recorded as flickering or altering its brightness, it was placed on lists of variable stars, interesting, but not necessarily exceptional. For decades, this quiet star nestled in the tiny constellation of Sagitta remained mostly overlooked. There were no fireworks, no mysterious signals, no odd chemical compositions that would immediately draw attention. And besides, in a sky filled with more than 150,000 known variable stars, what made V Sagittae any different? The answer, as it turns out, came with technology and time. As the century progressed, so did the tools of astronomy. More sensitive photometric techniques allowed astronomers to chart small changes in stellar brightness over time with far greater precision. Telescopes grew larger. Spectrographs became more refined. And most importantly, data began to accumulate, not just over nights or months, but over decades. It was in this accumulation that patterns began to emerge. By the late 20th century, astronomers noticed something strange about V Sagittae's variability. Its brightness wasn't just changing, it was increasing. And not just linearly, it was accelerating. This wasn't the erratic or pulsational variability seen in Cepheids or RR Lyrae stars. It was a systematic brightening, growing more dramatic with each passing year. That trend alone was enough to raise eyebrows, but it wasn't until deeper spectroscopic studies were performed that the true nature of V Sagittae began to reveal itself. High-resolution spectra showed emission lines and features characteristic of accretion disks, swirling rings of material spiraling into a compact object. This was a red flag. Accretion disks are common in close binary systems where one star is feeding material into the other. And when astronomers dug into the orbital dynamics of V Sagittae, they realized that what they were seeing was not a simple pulsating star, but a white dwarf feeding off a main sequence companion in a death spiral. The implications were massive. Here was a binary system with extraordinarily high mass transfer rates, a white dwarf growing in mass at a pace unmatched by almost any known system. The historical variability, once chalked up to random fluctuations, was now seen for what it truly was, the outward symptom of a catastrophic inner process. In 1999, the work of astrophysicists such as Bradley Schaefer and others brought V Sagittae into the spotlight. By studying the rate of brightening and comparing it against known models of mass transfer and accretion, they were able to determine that the system was headed toward a classical nova outburst. Not in some distant, abstract future, but within the 21st century. This realization shifted V Sagittae's status entirely. No longer was it just another variable star lost in the noise of the galaxy. It became a case study, a rare instance where we had caught a pre-nova system in its final decades. And thanks to its relatively nearby distance of about 7,800 light-years, the implications were clear. When this system goes nova, it will be visible to the naked eye, perhaps even during the day. With this discovery came a flurry of research. Archival images were revisited. Old photographic plates from the early 1900s were examined to track historical brightness. Observatories across the globe began targeting V Sagittae regularly. What had once been a forgotten star was now one of the most closely monitored nova progenitors in the sky. The story of V Sagittae's discovery is a powerful reminder of how science evolves, not just through revolutionary observations, but through the re-evaluation of old data in the light of new understanding. A star once dismissed as mundane turned out to be a ticking time bomb, hiding in plain sight for over a century. It also highlights how patient, cumulative science often yields the most extraordinary revelations. This wasn't the result of a single observation, but of many minds and many decades of watching, measuring, cataloging, and questioning. V Sagittae's exponential brightening wasn't noticed in a day, but once seen, it could never be unseen. Today, the star's history forms part of its intrigue. It reminds us that we can look at the same object for years and miss the bigger picture until we ask the right questions. And once we did, once we reanalyzed the decades of flickering and fading, brightness and dimming, we realized that V Sagittae wasn't just variable. It was dying. Violently. And on a schedule. Throughout the 20th century, V Sagittae remained largely in the background of astronomical research, a name on star charts, a minor flicker on photographic plates, catalogued and occasionally studied but never truly feared or celebrated. It was a star noted for its variability, yes, but not for anything that screamed cosmic catastrophe. And yet, hidden within decades of quiet data, a dangerous secret was building, one that would only become clear in retrospect, when patterns invisible to one generation became the unmistakable warning of impending doom to the next. From the early 1900s to the late 1990s, V Sagittae was observed sporadically through various sky surveys, often with gaps of several years or even decades between measurements. Back then, astronomers relied on photographic plates, which captured snapshots of the night sky on emulsion-coated glass. These plates weren't always precise by modern standards, but they offered a surprisingly rich trove of data. Many of these early observations showed V Sagittae fluctuating in brightness, sometimes fading, sometimes brightening slightly, and then returning to a baseline. The variations were minor enough to fall within the expected behavior of common variable stars. However, by the middle of the 20th century, more refined observations began to paint a different picture. Observatories equipped with photoelectric photometers, a technological leap from older photographic methods, started measuring V Sagittae's brightness with much greater accuracy. These instruments could quantify light output with a precision that allowed researchers to see subtle changes unfold over the span of years, changes that weren't random, but cumulative. It wasn't just that V Sagittae varied. It was getting brighter, and not just brighter, but brighter faster over time. Initially, the increase was so gradual that it barely registered as significant. A few hundredths of a magnitude here, a tenth there, within the noise range for many other stars. But in astronomy, long-term consistency is key. When decades of data were compiled, lined up chronologically, and corrected for observational error, a startling trend emerged. The light curve wasn't fluctuating randomly, it was trending upward. By the 1970s and 1980s, this long-term brightening could no longer be dismissed as observational error or minor variability. The system's luminosity had risen noticeably. It was no longer behaving like a classical variable star, it was becoming something else. Archival plates from earlier decades were revisited, digitized, and compared with contemporary measurements, confirming that the rise in brightness was real and persistent. This is where the story shifted dramatically. Astrophysicists began to take a closer look at what could be causing such an acceleration in brightness, and all signs pointed to mass transfer. As we now know, V Sagittae is a binary system where a white dwarf is stealing mass from a companion star. The system is extremely compact, with an orbital period of only 12.3 hours. That's dangerously close for a binary, and it indicated a high rate of gravitational interaction, tidal disruption, and mass exchange. The growing luminosity was a direct consequence of the increasing mass transfer rate. The white dwarf was pulling more material from its neighbor, and as that material spiraled into the white dwarf's accretion disk, it released vast amounts of energy, heating the system and making it shine brighter. By the late 1990s, long-term light curve studies, combining modern CCD photometry with earlier photographic and visual data, began to reveal the true shape of the star's rise, an exponential curve. This was the breakthrough. Unlike a linear increase in brightness, an exponential curve signifies runaway instability. It means the system isn't just growing brighter, but doing so at a rate that accelerates with time, a hallmark of systems approaching critical thresholds, like novae. It was around this time that a groundbreaking paper laid out the case that V Sagittae was heading for a nova, and not centuries from now, but in a time frame that intersects with our own. Estimates based on the brightness curve, orbital dynamics, and accretion rates pointed toward 2083 as the likely window, with some models allowing for variation of about plus or minus 11 years. This was unprecedented. Never before had astronomers been able to predict a nova with this degree of confidence and specificity. Other novae, like Nova Persei 1901 or Nova Cygni 1975, were observed only after they erupted, discovered by the sudden brightening of a seemingly innocuous star. But with V Sagittae, we weren't witnessing aftermath, we were watching the prelude in real time. The 20th century data, once ignored or misunderstood, suddenly became the foundation of a cosmic countdown. Observations from decades ago, painstakingly recorded by astronomers with much more limited tools, now became vital. They allowed scientists to calibrate the brightness curve, to confirm the exponential growth, and to verify the models of mass transfer and orbital decay. In fact, the strength of the nova prediction depends in part on just how consistent this brightness growth has been across the last century. A system that has shown a steady exponential increase for over 100 years is unlikely to plateau or stabilize suddenly. That consistency gives astronomers a rare degree of certainty that the process won't stop, that it will culminate in a visible nova, and that we are rapidly approaching the moment of detonation. Today, we view the 20th century observations not as historical footnotes, but as early warning signs, faint signals from a time when humanity didn't yet realize what it was watching. The astronomers of that era may not have known the star was a ticking time bomb, but thanks to their careful records, we now do. This transformation, from forgotten variable to imminent nova, was not triggered by a sudden change in the star, but by a change in human perception, powered by decades of cumulative data. It's a beautiful demonstration of how science is sometimes a slow, quiet revolution, how decades of patient observation can eventually light the fuse to cosmic revelation. The opportunity presented by V Sagittae is nothing short of extraordinary, a convergence of timing, technology, and understanding that may not occur again for centuries. In the vast, ancient sky, where stars are born and die across millions or even billions of years, It is almost unheard of to witness one preparing to explode on a timescale as human as our own. And rarer still is the ability to predict such an explosion with near certainty. Most novae take us by surprise. They appear suddenly in the sky, erupting without warning, often discovered by chance through patrol telescopes or even amateur stargazers. But V Sagittae is different. We aren't stumbling upon it mid-burst, we're watching the countdown. This makes it one of the most anticipated astronomical events of the 21st century. The significance cannot be overstated. We are watching a star in the final decades of its prenova phase, and we know when it will erupt, roughly around 2083, give or take a few years. In a universe where change is slow and unpredictable, this kind of foresight is a scientific rarity. Why is such prediction so difficult in the first place? Because novae, and even more so, supernovae, are chaotic and driven by nonlinear processes. The buildup of mass on a white dwarf is not always constant. The behavior of the accretion disk can vary due to magnetic fields, orbital instabilities, and unpredictable stellar wind interactions. Most binary systems that show variability do not reach the explosive conditions that V Sagittae is about to cross. In fact, the majority either stabilize, fall into low mass transfer phases, or simply flicker indefinitely without culminating in anything dramatic. Only in exceptionally rare cases does the mass transfer accelerate exponentially, the orbital period shorten, and the system evolve toward nova conditions with such obvious momentum. That's what makes V Sagittae a cosmic anomaly, and a golden opportunity for science. We have a front row seat to the final act of a nova in formation. Not only that, but the models tracking its exponential brightening are robust. They are backed by over a century of data, combining historical records, photographic plate analyses, CCD photometry, spectroscopy, and even modern simulations. And all the indicators align. The mass transfer rate is too high to maintain indefinitely. The brightness curve is rising too fast to suggest long-term stability. The system's orbit is decaying. The gravitational interaction between the two stars is tightening. The physics are screaming inevitability. For the astronomical community, this opens unprecedented possibilities. Scientists can observe and model the system in ways that were impossible with past novae, because those occurred without warning. With V Sagittae, we have time. We have decades to build more sophisticated instruments, to refine our models, and to prepare coordinated observational campaigns. Satellites like James Webb, future versions of Hubble, Earth-based observatories like the Vera C. Rubin Observatory, radio telescopes, infrared arrays, X-ray monitors, every spectrum can be trained on this one target in anticipation of the final moment. The explosion of V Sagittae will serve as a test of our understanding of stellar physics, a real-time validation or falsification of theories around mass accretion, nova ignition, and binary evolution. For decades, astronomers have relied on simulations to model how white dwarfs accumulate hydrogen and ignite it. But those simulations often run on assumptions. With V Sagittae, we'll get to see the real thing, live, in the sky, confirming or challenging everything we think we know. The nova will also give us the chance to witness how such explosions enrich the galaxy. Material ejected during the event will travel into interstellar space, possibly forming shells, shockwaves, or nebulae. Observing how this material behaves post-eruption can help us understand how novae contribute to the chemical evolution of galaxies, distributing elements like carbon, nitrogen, and oxygen, essential for the formation of planets and life. Even more uniquely, V Sagittae offers a rare chance to engage the public with science in a powerful way. When this nova erupts, it will not be some distant, abstract phenomenon. It will be visible to the naked eye, possibly even in daylight. Millions, if not billions, of people around the world will look up and see something that wasn't there the night before. News outlets will report on it. Schools will organize viewings. Social media will erupt with photos, commentary, and awe. And underlying all of that will be one unifying truth: we saw it coming. There's something profound in that. We often think of astronomy as passive, observing what's already happened, studying light from distant pasts. But this time, we're participants. We're awaiting an event, We've marked our calendars, not for a human occasion, but for a celestial one. It's like receiving an RSVP from the universe. Explosion coming, prepare to witness. And it's not just a scientific opportunity, but an emotional and philosophical one. How often do we get to know, with reasonable certainty, that something remarkable will happen in the sky in our lifetimes? How often do we get to tell children today, "You might grow up and see a star explode"? That kind of knowledge connects generations. It makes astronomy tangible, urgent, and deeply human. Some lucky individuals alive today will carry that memory, seeing a new star flare into existence, understanding its history, and knowing they were part of the generation that watched it happen. In an age when much of science can feel abstract or intangible, V Sagittae offers a direct, visceral experience, a once-in-a-lifetime intersection between humanity and stellar destiny. Of all the events visible in the sky, from eclipses to meteor showers to planetary alignments, this one is special. Because it's not just nature performing, it's nature letting us know in advance, as if the cosmos itself were inviting us to watch the end of a binary story 7,800 light-years in the making. V Sagittae isn't just a nova. It's a promise. And we're the first species to know it's coming. Even now, decades before the predicted eruption, V Sagittae has become the subject of intense and continuous observation. Across the globe, and even in space, telescopes are being trained on this unassuming point of light in the constellation of Sagitta. In the vast theater of stars, V Sagittae is no longer a background actor. It is the future protagonist of a cosmic drama we can already anticipate. And because we expect it to go nova within our lifetimes, it has earned a permanent place in the watch lists of observatories, both professional and amateur. From high-altitude mountain tops to orbiting satellites, the sky is being combed for every measurable detail. Large optical observatories, such as the Keck Observatory in Hawaii, the Very Large Telescope, VLT, in Chile, and the upcoming Vera C. Rubin Observatory, are keeping close tabs on its increasing brightness, spectral lines, and photometric changes. They aren't just observing it sporadically, they're recording time series data, plotting long-term curves, and comparing current behavior to historical archives. Every slight shift in magnitude or spectrum is scrutinized, because in a system this unstable, even tiny changes could be significant clues. Spectroscopy plays a vital role here. With high-resolution spectrographs, astronomers can break down the light from V Sagittae into its component wavelengths, essentially reading its chemical signature and motion. This allows them to measure the speed at which gas is being transferred, the temperature of the accretion disk, and the precise velocity shifts between the white dwarf and its companion star. Over time, this data provides a window into the accelerating spiral of doom that defines the system's final days. And every dataset adds a new layer to our models of what's about to happen. Meanwhile, radio telescopes such as those operated by the National Radio Astronomy Observatory, NRAO, and the Atacama Large Millimeter/Submillimeter Array, ALMA, are being employed to detect cooler, slower-moving gas and dust. These instruments are uniquely suited to study the denser regions of matter around the binary system, particularly in the accretion disk and in any jets or outflows that might be forming. Radio observations can reveal whether material is beginning to be ejected prematurely, a sign that the white dwarf is nearing a critical accumulation threshold. If V Sagittae starts to cough before the final roar, radio telescopes might be the first to notice. In addition to these heavy-hitting observatories, space-based telescopes are adding unparalleled data. The Hubble Space Telescope, for instance, has captured V Sagittae in multiple epochs, helping refine our understanding of its ultraviolet behavior and mass loss rates. The Gaia satellite, with its precise measurements of star positions and motions, continues to monitor the system's location and proper motion, providing a baseline for any future shifts following the explosion. And with the James Webb Space Telescope, JWST, now operational, astronomers have an infrared powerhouse capable of detecting the earliest signs of prenova heating or dust formation. But it's not just the big players. University observatories, citizen scientists, and amateur astronomers are all participating in this watch. Thanks to tools like the American Association of Variable Star Observers, AVSO, enthusiasts with high-quality telescopes can contribute valuable brightness data to a centralized database. These contributions, while small individually, are critically important over time. They fill in gaps between professional observations and help maintain the continuous vigilance needed to catch early signals of the nova's onset. Some amateur astronomers are even building dedicated photometric rigs, automated telescopes that observe V Sagittae night after night, recording magnitude changes with impressive accuracy. In the grand collaborative tradition of astronomy, this global web of observers functions like a network of sentinels. Each eye on the sky strengthens our collective readiness. As we get closer to the projected eruption date, this network of monitoring will only grow. More telescopes will begin long-term campaigns. More satellites will schedule regular sweeps. New instruments may be developed specifically for high-cadence observations of the system in its final pre-nova phase. We might even see coordinated multi-wavelength campaigns, where optical, X-ray, UV, IR, and radio observations are conducted in tandem to build the most complete picture possible. And there's another key motivation: to catch the precursors. While we expect V Sagittae to erupt around 2083, many scientists hope that the system will exhibit warning signs shortly beforehand: sudden spikes in brightness, erratic mass ejection events, or unusual shifts in its light curve. These would be invaluable not just for confirming the timeline, but for understanding the mechanics of nova ignition. If astronomers can detect the crackling before the flash, those final tremors before the stellar quake, they could refine nova models across the board, unlocking insights into dozens of other pre-nova systems. This level of attention and preparedness is unprecedented for a nova. Historically, most classical novae have been observed after the fact, leaving astronomers to piece together what happened from the fading afterglow. But V Sagittae is different. For the first time in modern astronomy, we have a ticking clock and a vast, coordinated scientific response that spans disciplines, continents, and instruments. Everyone is watching. And the importance goes beyond V Sagittae alone. The lessons learned in this watchful period will help scientists recognize other stars on similar paths. It may lead to earlier detection of other imminent novae, or even dangerous systems that could one day produce Type I supernovae, the kind of stellar explosions that shape galaxies and calibrate our measurements of cosmic expansion. In essence, we're not just watching a star. We're refining the very art of watching. V Sagittae is training us to anticipate the cosmos, to recognize signs before they erupt, to read the quiet build-up before the thunder. And as this star races toward its explosive fate, we, too, are racing toward a future where prediction becomes as powerful a tool as observation. The impending nova of V Sagittae isn't just a spectacle, it's a theoretical goldmine. For decades, astrophysicists have constructed models of stellar evolution, binary interactions, and mass transfer mechanics, but most of these models have been built in the dark, guided by fragmentary observations and the aftermath of stellar events. V Sagittae, by contrast, offers the rare chance to see theory collide with reality in real time. The explosion, when it comes, will serve as both a confirmation and a crucible, a stress test of our deepest assumptions about how stars live, interact, and die. At the heart of this system lies a white dwarf siphoning material from its larger, less dense companion. This alone challenges our understanding of binary mass transfer. In most binary systems, the more massive star evolves faster, expanding into a red giant and shedding its outer layers. But in V Sagittae's case, it's the smaller, denser remnant, the white dwarf, that dominates the interaction. It draws in hydrogen-rich material via a process known as Roche-Lobe overflow, where the bloated companion star spills matter past the gravitational threshold into the gravitational pull of the white dwarf. The fine details of how this transfer works, how the gas spirals inward through the accretion disk, how it's heated, and how angular momentum is exchanged, all of these processes are incredibly complex and, until now, largely theoretical. What makes V Sagittae such a scientific treasure is the extreme nature of its transfer rate. The mass transfer here is among the highest of any known binary system. Some estimates suggest rates up to 10 solar masses per year, vastly greater than typical cataclysmic variables. This is not a system gently bleeding, it's hemorrhaging. And the physics of such rapid mass transfer stretch existing models to their breaking points. For instance, how does the white dwarf respond to the sudden buildup of hydrogen on its surface? At what threshold does this thin layer of gas ignite in a thermonuclear detonation? What role do magnetic fields play in channeling this infall? These are questions astrophysicists are eager to answer, and V Sagittae will provide the data. It will also provide insights into stellar mergers. As the binary pair spirals inward, there's a chance that the system doesn't just ignite as a nova but eventually merges into a single, more massive object. If the white dwarf accumulates too much mass and the merger continues past the Chandrasekhar limit, approximately 1.4 solar masses, it could eventually trigger a Type I supernova, a far more powerful explosion. V Sagittae likely won't reach that stage in this century, but understanding the dynamics leading up to its nova could give us critical insight into how such mergers progress, and how frequently they occur across the galaxy. Even the shape of the explosion, the geometry of the ejected material, will help refine our understanding of how novae distribute mass and energy. Is the outburst symmetric, or is it lopsided due to the disk's rotation? Will it form a bipolar outflow, or will the companion star carve out strange cavities in the expanding shell? These questions touch on fluid dynamics, magnetic reconnection, and shockwave behavior in space, areas where real observational data are scarce but vitally needed. And then there's late-stage stellar evolution. One of the persistent questions in stellar physics is, how do stars evolve when they're locked in tight orbits with companions? Most models of stellar life cycles focus on isolated stars, but V Sagittae reminds us that companionship can rewrite fate. The companion star, losing mass at such an aggressive rate, is no longer following a normal evolutionary track. Its internal pressure, temperature, and nuclear fusion processes are being altered as it is slowly stripped apart. Meanwhile, the white dwarf, normally a stable stellar remnant, is being dragged back into chaos by the very mass it's consuming. This unique interaction will allow scientists to test and revise models of how close binaries evolve over time. Many phenomena in astrophysics, from X-ray binaries to gravitational wave sources, arise from such tightly bound stellar pairs. Watching V Sagittae evolve over the next few decades will not only tell us about novae, but about entire classes of compact binary systems, informing our understanding of black hole formation, neutron-star collisions, and even kilinovae. The nova event will also provide opportunities to study thermonuclear runaway reactions in extreme conditions. The ignition on the white dwarf's surface is expected to result from a rapid chain reaction where hydrogen fusion occurs uncontrollably. The exact conditions required for such a runaway, including pressure thresholds and the balance between accretion heating and radiative cooling, remain murky in the theoretical realm. V Sagittae's nova will offer a real-world laboratory to examine those mechanics. Furthermore, this nova will give us critical clues about the chemistry of stellar ejecta. What elements are thrown into space? How are they distributed? Does the explosion produce significant amounts of heavier elements? And how does this material integrate into the interstellar medium? By analyzing the spectra of the expanding shell, scientists can measure the abundance of elements like nitrogen, carbon, and oxygen, helping answer long-standing questions about chemical enrichment in galaxies. There's also the question of dust formation. Novae often eject material that cools and condenses into dust grains, which can later seed new stars or planets. But under what conditions does this dust form? What shapes and compositions dominate? Observing V Sagittae before, during, and after its eruption, especially in the infrared, can answer these questions. And because we know when the nova is coming, scientists can position instruments in advance to monitor dust formation as it happens, not just in the aftermath. In short, V Sagittae is a case study for dozens of astrophysical processes at once. It straddles disciplines, from thermonuclear physics to fluid dynamics, from stellar chemistry to orbital mechanics. Theoretical astrophysics, which often labors in the abstract, will have in V Sagittae a rare chance to confront nature's version of the equations. And unlike most events in the cosmos, we're not late to the scene. We're early. We're ready. And that means the science we extract from this explosion will be deeper, richer, and more transformative than nearly any nova in modern memory. This is why researchers are preparing now, years ahead of the eruption. V Sagittae isn't just an object of wonder, it's a cosmic proving ground, one that will shape our theories for decades to come. In the laboratories of Earth, we can recreate only fragments of stellar conditions. But in V Sagittae, the universe is building the experiment for us. And when the detonation comes, it will not only light up the night, it will illuminate the limits of our knowledge. Despite the looming explosion of V Sagittae, and the immense energy it will release into the cosmos, Earth is in no danger. Though the idea of a star going nova sounds apocalyptic, and in a way, it is for the stars involved, it's important to understand just how vast space is, and how the energies involved behave over such unimaginable distances. V Sagittae sits approximately 7,800 light-years away from Earth, nestled in a quiet pocket of the Milky Way in the small constellation Sagitta. And in astrophysical terms, that's safely distant. When the nova event occurs, it will release a torrent of light, radiation, and high-velocity stellar debris. But that debris won't be heading our way with any force that can harm us. Unlike nearby supernovae, whose X-rays and gamma rays could potentially disrupt planetary atmospheres if they occurred within 50 or 100 light-years, V Sagittae's detonation simply doesn't pack that kind of proximity-based punch. Its outbursts will be visible, yes, and perhaps stunningly so, but it will not interact physically with our atmosphere, biosphere, magnetic field, or orbit. We will only be observers, not participants. To understand why we're safe, it helps to look at how energy behaves over distance. Radiation intensity follows the inverse square law. As it travels outward, it spreads across an ever larger sphere. This means the further you are from a radiation source, the weaker it becomes, exponentially. At nearly 8,000 light-years, even powerful bursts of electromagnetic energy from V Sagittae's nova will have dissipated to negligible levels by the time they reach Earth. The light we'll see will be intense in a visual sense, not a hazardous one. It will dominate the night sky, potentially even be visible in the day depending on the peak magnitude, but it won't come with searing UV or gamma-ray radiation capable of harming life. In fact, the kind of radiation we'll detect will mostly be in the optical, ultraviolet, and possibly X-ray ranges, mostly useful to astronomers with dedicated detectors. Earth's atmosphere and magnetosphere are also excellent shields. High-energy particles, if any make it this far, will be blocked or redirected just like the solar wind is filtered every day. There are no known mechanisms by which a nova at V Sagittae's distance could cause significant effects on Earth. No climate change. No radiation sickness. No geomagnetic storms. It's also worth noting that this will not be a supernova, which is a much more destructive event involving the total collapse or detonation of a massive star. V Sagittae will explode as a classical nova, a surface-level thermonuclear event on a white dwarf triggered by accumulated hydrogen from a companion star. While powerful, it's orders of magnitude less energetic than a supernova. Even if the system someday does evolve into a supernova, which may take tens of thousands or even millions of years, it will still be too far to affect Earth physically. Astronomers have long studied the impact radius of dangerous cosmic explosions, and the consensus is that supernovae need to occur within 30 to 50 light-years to pose any real risk to Earth's biosphere. V Sagittae is more than 150 times further away than that conservative estimate. So, what can we expect when it finally goes nova? A light show, essentially. A brilliant, sudden point of light in the sky, rivaling Venus or even the Moon at peak brightness, slowly fading over days and weeks. For a short time, it might even cast shadows at night. But that's the extent of its influence. It won't disrupt satellite communications. It won't damage power grids. It won't trigger earthquakes or volcanoes. It won't affect animal behavior any more than a full moon might. It will be, in the most literal sense, harmless all. And if there's any doubt about how often we experience such cosmic events safely, consider that classical novae occur in our galaxy roughly 20 to 30 times per year. Most of them go unnoticed by the general public because they happen behind the veil of interstellar dust or in crowded star fields. V Sagittae is simply the first one we're expecting, and expecting so vividly that its approach feels like a monumental event. And it is. But not because it poses a threat. Still, questions like, will it harm Earth? Are important and common. Public concern often spikes when cosmic events enter the media spotlight. For this reason, astronomers and space agencies have already taken care to explain V Sagittae's safety. Organizations like NASA, the European Southern Observatory, and institutions such as the Royal Astronomical Society have reiterated that this nova, while brilliant, will not affect Earth's physical systems. Some have even gone further, emphasizing the educational opportunity in observing such an event without risk. In classrooms, this nova could become a moment of unity, where millions of students across the globe observe the same cosmic flash, learn the same science, and understand the rhythms of stellar life and death in a deeply personal way. It will be the closest most people come to witnessing a celestial firework in real time, without a telescope, without fear. We live on a planet bathed constantly in light from far-off explosions, ancient supernovae, variable stars, gamma-ray bursts, and quasar flares. That light, diluted by vast distances, is harmless by the time it reaches us, mere photons that tickle our eyes or strike a CCD sensor. V Sagittae's outburst will be no different, except for the brilliance and the timing. It will not scorch, shake, or blind. It will simply illuminate, and remind us of the power of the cosmos, seen from a place of perfect safety. When the moment finally arrives, sometime around 2083, a new light will pierce the sky. To the naked eye, it will seem as though a new star has simply appeared overnight in the constellation of Sagitta, catching stargazers, casual observers, and even many unaware people off guard. This is how V Sagittae will introduce itself to the world, not with thunder or a cosmic roar, but with a quiet, unblinking blaze. For many, it will be indistinguishable at first from the brightest stars we've always known, Sirius, Vega, Arcturus. But astronomers, sky watchers, and those who have been anticipating this moment for decades will know instantly, this is it. What we will see depends greatly on timing, viewing conditions, and location on Earth. But make no mistake, once V Sagittae erupts, it will be unmissable. The nova is expected to reach a magnitude of -2 or even brighter, which would make it shine more brilliantly than any star in the sky. It could rival Venus in brightness, or in the most optimistic projections, even approach the apparent magnitude of the Moon. And it will do all this not slowly, but within days, as the thermonuclear explosion spreads across the white dwarf's surface and hurls energy into space. The first thing people will notice is that a new star has appeared where none was visible before. In regions with dark skies, V Sagittae will dominate the evening and pre-dawn hours, casting a pale glow that some may mistake for a planet. In fact, it may become a common question during the event. Is that Venus? But Venus never appears in the middle of a constellation like Sagitta, nor does it rise in the same position for weeks on end. This will be something different. Something never seen before in living memory. To the unaided eye, V Sagittae will appear as a brilliant, white or slightly yellowish star. Unlike planets, which shine with a steady light, stars twinkle because their point source light is distorted by Earth's atmosphere. V Sagittae will twinkle too, but not like the others. Its brightness will be intense and concentrated. Even from light-polluted urban areas, it may remain clearly visible, standing out starkly against the usual faint canopy of stars. Those using telescopes or binoculars will be treated to even more wonder. In high magnification, the nova will still appear mostly as a point of light, but surrounding it, astronomers may begin to detect a growing halo of ejected gas. Over time, days, then weeks, the material flung out from the explosion will expand outward at speeds exceeding thousands of kilometers per second, eventually forming a shell or nebula. Some telescopes might even begin picking up spectral signatures of various elements being expelled: hydrogen, helium, carbon, nitrogen, each glowing in distinct colors, revealing the nuclear fury that took place. There may also be variations in brightness over time. After the initial peak, V Sagittae will begin a slow fade, but it won't disappear right away. For weeks, perhaps even a couple of months, the nova will remain visible in the night sky, a lingering reminder of the explosion's power. Some nights it may seem dimmer, other nights it may pulse slightly brighter, depending on atmospheric conditions and how the shockwave and expelled material evolve. But every night, it will be there, an undeniable, radiant wound opened in the fabric of the stars. For those with access to long-exposure cameras or astrophotography setups, the eruption will be even more surreal. A simple DSLR on a tripod might capture the nova flaring like a spotlight against the star field, surrounded by faint structures that the naked eye cannot perceive. As time goes on, deeper exposures may start to show faint nebular formations, echoing the classical remnants left behind by earlier novae throughout the Milky Way. Astronomers may even capture jets or bipolar outflows, depending on the geometry of the explosion. These features, beams or lobes of gas being ejected preferentially along certain axes, could tell us about the orientation of the accretion disk and the magnetic field shaping the eruption. If such outflows occur, they might show up in radio, ultraviolet, and X-ray observations first, but some may eventually become optically visible. The sheer public reaction will be an event in itself. Major news outlets will report it within hours of confirmation. Social media will flood with blurry smartphone photos of the new star, as people around the globe step outside to witness the spectacle. Nightly news segments will explain the science. Astronomers will give public lectures and live-stream telescope views from observatories worldwide. For a brief window of time, the entire planet will look up together. And this will likely be the first nova event in modern history that is predicted, monitored, and live-streamed globally, before, during, and after the eruption. Citizen science projects will spring up. Amateur astronomers will coordinate with professionals to log changes in brightness. In a way, it will be the first digital age nova, where the entire life cycle of the event is documented in real time, across all corners of the globe. Some observers may report changes in sky brightness or even being able to read by starlight, particularly in rural areas during the nova's peak. Historical records describe past novae and supernovae that were so bright they cast shadows. While V Sagittae's explosion isn't expected to be quite that intense, it's not impossible that it will come close. For many, the psychological effect, the surrealness of a new star appearing, will be deeply profound. And let's not forget the simple, quiet moments, people sitting on rooftops or lying in fields, staring into the night and seeing something that hasn't been there before. A new star. A new light. A once-in-a-lifetime moment. Though astronomers have projected the eruption of V Sagittae to occur around the year 2083, this prediction comes with a necessary caveat: the exact timing is still uncertain. The nature of stellar evolution, especially in such dynamic and chaotic systems as rapidly interacting binaries, does not conform neatly to human calendars. While all current models point toward the early 2080s as the window in which this system will erupt into a nova, the actual event could arrive a few years earlier, or a few years later. In cosmic terms, a decade of uncertainty is barely the blink of an eye. But for us, waiting on the edge of our seats, it introduces a kind of thrilling unpredictability. To understand why the date is not set in stone, we need to dive deeper into the variables and complex physics that govern the evolution of this binary system. The exponential brightening of V Sagittae has been one of the key metrics in estimating its trajectory toward a nova. This brightening, caused by the accelerating mass transfer from the companion star to the white dwarf, is a signature of growing instability. It is like watching a balloon inflate, at first slowly, then more quickly, and eventually, inevitably, pop. But predicting the precise moment of that final burst requires knowing exactly how much mass the white dwarf needs to accumulate to trigger runaway thermonuclear ignition. This critical mass isn't a fixed number. It depends on factors like composition, surface temperature, magnetic fields, and the exact structure of the accreted hydrogen envelope. Even slight changes in these properties can shift the ignition point forward or backward in time. Then there's the complication of variability in the mass transfer rate. The donor star isn't losing mass at a perfectly steady rate. It fluctuates due to internal pulsations, stellar wind variations, and interactions with the white dwarf's magnetic field. This variability introduces unpredictability into the system's timeline. A sudden burst of increased transfer could push the white dwarf to nova conditions faster than expected. On the other hand, a brief period of reduced transfer, perhaps caused by a shift in the companion star's outer layers, could delay ignition by years. Add to that the behavior of the accretion disk, a swirling halo of gas that forms around the white dwarf from the stolen material. This disk isn't static. It can warp, thicken, thin out, or even eject material in minor outbursts. These changes affect how efficiently the white dwarf gains mass, and therefore how quickly it approaches nova conditions. If the accretion disk becomes unstable, it could either accelerate or decelerate the buildup, subtly nudging the explosion date in either direction. Even the internal physics of the white dwarf itself are not entirely predictable. Scientists still debate how magnetic fields and differential rotation within the dwarf influence the timing of surface ignition. We may find, through continued observation, that our models slightly misrepresent the true behavior of this system. If so, it's entirely possible the nova could surprise us, either arriving earlier, perhaps in the late 2070s, or dragging its feet into the 2090s. This uncertainty is not a failure of science but rather a reflection of how frontier science works. V Sagittae is teaching us as we observe it. Every new data point, each flicker of brightness, each shift in spectrum, is recalibrating our models. The original estimate of 2083, proposed in a 2020 research paper by astronomers Bradley Schaefer and Juan Frank, is based on a meticulous analysis of decades of data showing an exponential rise in brightness. They modeled this trend mathematically and found that it intersected with critical nova conditions somewhere around that year. But even they acknowledged a possible window of plus or minus a decade, depending on physical nuances we may not yet fully understand. That's why astronomers aren't waiting for 2083 to start paying attention, they're observing now. The nova may come sooner, and scientists want to catch every sign leading up to it. There's hope that in the final years, V Sagittae will offer telltale precursors, changes in light curve shape, sudden ejections of gas, or shifts in orbital velocity. If and when these signs begin, the scientific community will know that the timeline is narrowing. Until then, the estimate remains a probabilistic forecast, not a countdown clock. From the public's perspective, this variability means we must remain vigilant but patient. Much like a volcano building pressure, the eruption is inevitable, but not precisely schedulable. Media headlines in the coming decades may proclaim the nova is due any day now. And while that will technically be true, the day could still be 5 or 10 years away. What's more important is the certainty of the event, not the exact timestamp. It will happen. We just don't know exactly when. This uncertainty adds to the drama, to the emotional intensity of watching a star evolve. There will be nights in the 2070s and 2080s when astronomers peer into their scopes with a mixture of excitement and tension. Is this the night? They'll wonder. It could happen while someone is asleep. It could burst into view during a school day, a dinner, a commute home from work. That randomness, that inability to predict the moment of transformation, is part of what makes it so special. And when the nova does arrive, the world will erupt in shared awe. But until then, we wait, knowing that whether it's 2083 or 2089, the end of V Sagittae as we know it is written in the stars. The timing may shift, but the destination is fixed, a sudden, fiery burst of light that will stun the sky and echo through the annals of astronomy forever. As the countdown to V Sagittae's explosive finale continues, scientists have turned to one of their most powerful tools: computer simulations. With a system as dynamic and complex as this binary star nearing detonation, it's impossible to predict every nuance through observation alone. The physics involved spans an extraordinary range, from nuclear fusion at the white dwarf's surface to the delicate gravitational dance between the two stars, to the way ejected gas will move through space after the nova. Fortunately, with modern computing, we can run incredibly detailed models that simulate how each of these layers unfolds, not just to understand the star's fate, but to forecast what Earth-based observers will actually see when it happens. These simulations begin with the structure of the binary system itself. Astronomers input decades worth of real observational data, orbital period brightness curves, mass transfer rates, stellar temperatures, and compositions, into physical models that replicate how the system evolves over time. One of the first goals is to simulate the mass transfer from the companion star to the white dwarf. This isn't a gentle process. The donor star, swollen from internal pressure, is spilling its hydrogen-rich outer layers across a gravitational boundary known as the Roche lobe, allowing the white dwarf to cannibalize it. Simulations trace how this matter flows, forming spirals, disks, shocks, and how the disk around the white dwarf evolves in shape, density, and temperature over time. As the white dwarf accretes more mass, simulations predict how pressure and temperature build on its surface, and how close it is to triggering a thermonuclear runaway. This is where thermodynamic models take over. They simulate nuclear fusion reactions, how the hydrogen layer atop the white dwarf is compressed until it reaches ignition conditions, setting off a chain reaction. These calculations are incredibly intricate, relying on the equations of state for degenerate matter, radiation transfer, and explosive hydrodynamics. Once ignition occurs, a second wave of modeling takes over, the hydrodynamic explosion itself. Scientists simulate how the thermonuclear energy spreads across the white dwarf's surface in seconds, vaporizing the hydrogen layer, ejecting it outward in a violent blast, and shaping the nova's outer shell. These models must capture the behavior of gases at extreme temperatures and velocities, thousands of kilometers per second, while incorporating effects like shockwaves, collisions with previously ejected material, and the formation of bipolar outflows or asymmetric shells. These simulations also attempt to model light curves, graphs that show how the nova's brightness will rise, peak, and fade over time. The exact shape of this curve depends on many factors: the amount of mass ejected, the temperature of the explosion, the size and orientation of the accretion disk, and the amount of dust or gas that might briefly obscure the light. By tweaking input parameters, researchers can predict different visual outcomes: a sharp, dramatic peak that fades quickly, or a slower, plateau-like brightness that lingers in the night sky. These light curves help scientists understand not just when the nova will occur, but what kind of celestial performance we'll witness from Earth. To bridge the gap between theoretical results and what sky watchers will observe, simulations also factor in Earth-based perspectives. They calculate how bright V Sagittae will appear at various altitudes, under different atmospheric conditions, and from both hemispheres. They simulate spectral output, which wavelengths of light will dominate at different stages of the eruption, and predict how telescopes might detect emission lines from ejected elements like hydrogen, helium, carbon, or oxygen. Some simulations even recreate the expected images, producing visualizations of what we might see through telescopes in the hours and days after detonation. One particularly valuable simulation approach involves multi-wavelength modeling. V Sagittae's explosion won't just emit visible light, it will burst across the electromagnetic spectrum, from radio waves to gamma rays. Researchers use simulation software to estimate how each band will behave. Will there be strong ultraviolet emissions? Could X-rays be detectable with space-based instruments? How might infrared telescopes observe the cooling of the gas cloud and potential dust formation in the aftermath? These questions aren't just academic, they're critical for mission planning. If we know, for example, that infrared emissions will peak 3 days after the explosion, telescopes like JWST or SOFIA's successors can be positioned accordingly. In some simulations, researchers are even going a step further, testing scenarios in which V Sagittae becomes a supernova candidate after the nova. While that final fate lies far in the future, modeling these longer-term paths allows us to better understand what happens when white dwarfs continue to accrete mass over millennia. Some models suggest that novae like this may be part of a stepping stone to Type Ia supernovae, explosions so powerful they outshine entire galaxies. V Sagittae offers a perfect lab to test that idea, and simulations help extend our vision beyond what current observations alone can provide. Simulations are also instrumental in studying variability and instabilities before the explosion. Some models explore how the white dwarf might shed material intermittently, creating mini outbursts or flickers in the years leading up to the nova. Others examine whether gravitational interactions or magnetic forces might cause sudden spikes in brightness or orbital shifts. By testing millions of scenarios in virtual environments, scientists can identify potential early warning signs, signals that the nova is imminent. This is critical because if such signs are detected in real data, astronomers could trigger a rapid response observing campaign with telescopes around the world. Of course, simulations aren't perfect. They rely on assumptions, and even the best models must simplify the underlying physics to make computation feasible. No simulation can capture every molecule or photon. But with increasing computational power, especially the rise of supercomputers and AI-assisted modeling, these simulations are getting more accurate, more detailed, and more useful every year. Some research teams are even training machine learning algorithms to identify patterns across massive datasets of previous nova and binary star behaviors, in hopes of refining the prediction for V Sagittae's timeline. The synthesis of all these models, hydrodynamic, thermonuclear, observational, spectral, is creating a virtual V Sagittae, a digital twin that astronomers can interrogate, manipulate, and learn from before the real event unfolds. It's a remarkable convergence of data, physics, and computation, all in service of understanding what will be one of the most astonishing celestial events of the 21st century. And when the sky erupts, these simulations will either be validated or challenged in dramatic fashion. A perfect match between prediction and observation will confirm our models of stellar interaction. A mismatch will teach us something new. Either way, science advances. After the brilliance fades and the gas shell expands into the cold void, the story of V Sagittae will not end, it will simply enter its next chapter. The nova explosion, though spectacular, is not the final act for the system. Like a breath held and released, the eruption is a temporary outburst, and once the expelled material thins into the interstellar medium, the binary will remain, transformed, but intact. What happens next could shape its long-term destiny. Whether it will fade quietly into stellar senescence or march steadily onward toward a far more violent and final fate, a Type I supernova. Immediately following the nova, the system will undergo a period of dramatic adjustment. The white dwarf, having burned off the accumulated hydrogen layer in a flash of thermonuclear fury, will cool again, its surface returning to stability. But this won't be an immediate process. The white dwarf will remain hot and luminous for some time, and the surrounding space will continue to glow with ionized gas, visible in certain wavelengths, particularly ultraviolet and X-ray, as the last traces of the eruption settle. Astronomers observing the system will be looking closely at the remnant shell of gas. Much like the remnants of other novae, such as GK Persei or RS Ophiuchi, the expelled material may continue to expand outward, forming a visible shell or halo that telescopes can monitor for years. This shell could carry key information about the composition of the nova, the velocity of the outflow, and the geometry of the ejection. Was it spherical, or did it form jets? Was the explosion symmetrical, or lopsided due to the presence of the accretion disk and magnetic fields? In the long term, the white dwarf will once again begin accreting material from its companion. This is the essence of V Sagittae's binary identity, a never-ending cycle of theft and tension. The companion star, still overflowing its Roche lobe, will continue to donate matter. The nova doesn't reset the clock entirely. It merely clears the surface of the white dwarf and sets the stage for another cycle of mass transfer. In fact, this resumption may be faster than before, depending on how much mass the donor star still holds and how the explosion affects the system's orbital separation. Some simulations suggest that mass transfer might temporarily slow after the nova due to changes in the system's angular momentum. The ejected material could carry away angular momentum, increasing the orbital separation slightly, which in turn reduces the gravitational pressure driving the mass transfer. This would give the system a chance to breathe, a brief period of relative calm before the gravitational spiral resumes. But this delay would be temporary. Over time, gravitational radiation and magnetic braking, forces that slowly rob the system of angular momentum, will draw the two stars closer once more, reigniting the accretion process. Eventually, if the white dwarf continues to grow in mass through subsequent nova cycles, it may approach the Chandrasekhar limit, the critical threshold of about 1.4 solar masses beyond which a white dwarf can no longer support itself against gravitational collapse. If it ever reaches this mass, it will no longer erupt in small, surface-level explosions. Instead, it will collapse inward and detonate as a Type I supernova, a far more powerful and destructive event that completely obliterates the white dwarf. But this pathway is still uncertain. Not all white dwarfs that undergo novae reach the Chandrasekhar limit. In many cases, they lose as much mass during the nova as they gain through accretion, or the accretion slows enough that equilibrium is maintained. For V Sagittae, this future remains an open question. It may simply settle into a cycle of periodic novae, flaring every few thousand or tens of thousands of years, without ever crossing the critical mass. Another possibility is that the system will merge entirely. As the orbital decay continues, the donor star may become so depleted, so drawn out by tidal forces, that it eventually falls entirely into the white dwarf, forming a single object. This merger process could produce another explosive event, possibly even mimicking the power of a true supernova, though not following the standard Type I pathway. These are known as .I supernovae, or .1a events, shorter-lived, less luminous versions that may still signal the final act of binary white dwarfs and their companions. In some post-nova systems, the aftermath leads to permanent reconfiguration. The companion star, having lost much of its outer envelope, may become hotter and more compact, essentially a helium star or proto-white dwarf in its own right. The mass loss also affects its magnetic activity, possibly altering flare cycles or disrupting stellar winds. In extreme cases, the companion might shrink to the point where accretion becomes difficult, slowly halting the cycle altogether. This would cause the nova system to become dormant, fading from view as it quietly drifts among the stars. Astronomers will be watching for all these signs in the years and decades following V Sagittae's eruption. They'll track how quickly the brightness fades, how the color changes, and how the system behaves across different wavelengths, from optical to X-ray to radio. They'll map the evolution of the ejected shell and look for spectroscopic fingerprints that might reveal whether the white dwarf is gaining or losing mass in the long term. There's also the chance that the nova will give rise to new structures in space, such as dust formation. As the gas cools, elements like carbon and oxygen may condense into tiny grains, forming cosmic dust that drifts outward into the interstellar medium. This dust could, over millions of years, seed the formation of new stars, planets, and possibly even life. In this sense, V Sagittae's violent transformation is not an end, but part of the eternal cycle of stellar death and rebirth, a nova that enriches the cosmos. Ultimately, what happens after the nova will answer one of the most profound questions in astrophysics. Can white dwarfs grow through nova cycles, or do they shed more mass than they gain? This question directly ties into our understanding of supernova origins, galactic chemical evolution, and even the use of Type I supernovae as standard candles for measuring cosmic expansion. If V Sagittae turns out to be a stepping stone to a supernova, it may one day play a role in refining the Hubble constant and reshaping our understanding of the universe's fate. But for now, all we know is this: when the explosion is over, the stars will still be there. Changed, yes. Scorched, scarred, and stripped. But still bound by gravity. Still spiraling, evolving, destined for another chapter. For the first time in human history, we are not just peering into the vast theater of space hoping to catch a fleeting glimpse of a celestial drama. We are holding a ticket with a tentative date printed on it. A date in the not-so-distant future when we will witness a star change before our eyes. That star is V Sagittae, and its scheduled eruption represents something profound, the moment when cosmic evolution aligns with human anticipation. Traditionally, astronomy has been a science of patience. Phenomena like supernovae, eclipses, or comets have been observed as they occurred, often without warning. We've catalogued events after the fact, piecing together light curves and remnants long after the flash was gone. But V Sagittae breaks this mold. It's not a discovery by accident or a surprise event caught in a survey. It is a transformation we forecast. A celestial change we are awaiting together. It's as if the universe sent out an invitation and we, for once, got it early. That alone marks a shift in our relationship with the cosmos. V Sagittae will not be an unexpected guest in our sky. It will be the culmination of decades of data, refined simulations, and careful astrophysical theory. When it erupts, we will have context. We will know what we are seeing. And that knowledge turns what might otherwise be a bright dot in the sky into something monumental, a known transformation, a death and renewal event in real time. For astronomers, this is as close as one gets to a live cosmic experiment. By marking the calendar, whether it's 2083 or a few years off in either direction, we've effectively scheduled a stellar eruption. That gives researchers unprecedented time to prepare instruments, coordinate global observations, and design studies that will maximize what we can learn from the event. Everything from high-energy space telescopes to backyard DSLR cameras will be pointed at Sagitta. Across continents and disciplines, a vast, decentralized effort will converge on a single patch of sky. And this anticipation is not just scientific, it's cultural. Future generations will grow up knowing that a star will explode in their lifetime. Children born today will be in their 50s when it happens, middle-aged people with memories of their first look at the sky, perhaps sparked by stories of the nova that's coming. Educators and parents will be able to say with confidence, "You'll live to see a star burst into light." Not a prediction of doom, but a forecast of wonder. That kind of certainty is rare, and it has the power to inspire in ways we haven't fully seen before. The societal ripple of such an event will be extraordinary. Unlike past celestial events, which were often known only to scholars or watchers of the stars, this one will be announced years in advance. Public outreach campaigns will be launched. Documentaries will be filmed in anticipation. Apps will be made so people can track the nova countdown in real time. School curriculums will include units on stellar evolution framed around V Sagittae. It won't just be astronomy, it will be a global cultural moment. Imagine the day it happens. News anchors cutting into their broadcasts to announce it. Social media feeds flooded with photographs. Thousands of live streams from observatories and amateurs alike. Astronauts aboard the International Space Station gazing down at a world collectively looking up. Children who've never noticed the stars before staring wide-eyed at a light in the sky that wasn't there the day before. People making wishes on it, photographing it, building memories around it. A shared, global experience of awe. And even beyond the initial flash, the event will unfold over weeks, giving people the chance to return, night after night, to observe the fading beacon. They'll track its decline, note its slow fade from prominence, and reflect on the reality that they just witnessed something that will never happen again in quite the same way. That star, in that configuration, only had one final eruption. And they saw it. In that sense, V Sagittae will become a marker in human history. A timestamp. A moment when the cosmos aligned its rhythm with our own. We will be able to say, "That was the year the sky changed." Not metaphorically. Not mythically. Literally. A visible object in the heavens, once too faint to notice, suddenly flared into brilliance, and then dimmed away, leaving behind not just astrophysical data, but a collective memory etched into human consciousness. And while V Sagittae itself is not the only star of its kind, the uniqueness lies in the prediction. There will be other novae, other supernovae, other galactic surprises. But never before has humanity awaited a nova with such certainty and clarity of timeline. It is a living testament to how far our science has come, that we can read the future in the light of stars. And long after its light has dimmed, the memory will linger. Stories will be told. Books will be written. A generation will recall the night when the sky grew brighter than it had in centuries. Astronomers will pore over the data for decades. And somewhere out in the galaxy, the light from that explosion will still be traveling, racing through space, toward other civilizations that may one day look up and wonder what once happened in our part of the cosmos. One day in 2083, or perhaps a few years earlier or later, you may find yourself standing beneath the stars. It could be on a quiet night, walking your dog. Or on a rooftop with friends. Maybe it's the end of a long day, and you look up simply out of habit. And then you see it. A star that wasn't there the night before. A new, blazing point of light puncturing the sky. Not a planet, not a comet, not a trick of the eye, but a star, bursting forth with a brilliance no one alive has ever witnessed. That moment will mark the arrival of V Sagittae's long-anticipated nova, and the beginning of one of the rarest and most profound shared experiences in the history of humanity. We often think of stars as fixed, eternal, dots that remain unchanged across generations. They outlast empires, civilizations, even species. They burn for billions of years, far beyond our lifetimes. But V Sagittae is different. It's a reminder that the stars do change. That the universe, even in its vastness and cold silence, is alive with motion, drama, and transformation. And for once, we are not just passive witnesses, we are prepared. We know it's coming. We've calculated, simulated, observed, and predicted it. We've even written it into our future calendars. The eruption of V Sagittae won't just be an astronomical phenomenon, it will be a symbol of human progress. A signal that we, a species bound to the surface of a small planet, have learned to read the language of the stars well enough to predict their future. That we can anticipate an event happening 7,800 light-years away, involving forces beyond anything we can experience on Earth, and know, within a few years, exactly when it will unfold. This star will be born in fire, not in the calm, glowing expansion that marks stellar birth from clouds of gas, but in a thermonuclear flash that will hurl matter into space and carve a new chapter in the life of a binary system. For weeks, it will shine down on our world. It may outshine everything in the sky save for the moon. It may be bright enough to cast shadows, to see it in daylight, to track its fading trail each evening like a cosmic countdown of its own. And while we marvel at the beauty, science will be hard at work. Telescopes in orbit and on Earth will collect every photon they can. Instruments will measure radio waves, X-rays, ultraviolet, infrared, all painting a multispectral portrait of a stellar eruption in action. Data will pour in faster than ever before, archived and shared globally in real time. Students, scientists, artists, and the curious will unite around one question: did you see it? This moment will resonate through time. The nova will become a generational landmark. People will tell their grandchildren, "Yes, I saw the star that wasn't there. The one they said would come." It will shape careers, launch new fields of research, and inspire the next wave of skywatchers. It will humble us with the scale of the universe and elevate us through the unity of shared wonder. We will look up, not with fear, but with awe, and feel something bigger than ourselves. V Sagittae is our cosmic countdown. It's a reminder that even in a universe so immense, so ancient, so seemingly indifferent, we can find meaning, connection, and purpose. That we can mark a date in our future and say with wonder, that is when the sky will change. And when that day arrives, whether you're holding a telescope, a camera, or just your breath, know that you are witnessing history. Not written in books, but across the very fabric of the cosmos. A story 7,800 years in the making, finally arriving on Earth in a flash of light. The day the sky changes will not be one of endings. It will be one of beginnings. Because after that star fades, we will still be looking up. Still searching. Still learning. Still wondering. And somewhere out there, perhaps, another star will begin its silent countdown, just waiting for us to notice. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.